All right, so I am going to go ahead and kick off the event. Welcome everyone to the California AI Summit. I'm super excited for this whole morning, afternoon. Thank you to everyone who's been able to log on so far. And I'll just start with the opening ceremony. So on behalf of the California chapter of the Girls Computing League, I'd like to welcome you to this event, and we're very excited to be hosting this. Before we get started, I'd like to take a minute to thank our sponsors, Slingshot, REPL.IT, Linode, 1Password, Balsamic, and No Starch Press for providing the awards for the AI Ideathon. We truly appreciate their support. And I would also like to introduce our team for this event. So I'm going to start off with myself, and then we'll go from left to right. So my name is Ashley, and I'm the California chapter leader for the Girls Computing League. I've been with GCL for about a year, and I also lead the GCL Scholars Program. I'm super excited for this event. I know we've been planning this for many months, and many of you have been submitting your pitches many months in advance. And I've always wanted to support STEM education for young students. And I believe that this event is going to be a great way to propel all of you in your careers within STEM.
Hi everyone, I'm Yoshu Gedem, and I'm the lead event organizer from Washington in Girls Computing League. And I'm excited for all the events that we have planned for today, and I hope everyone enjoys them.
Hi everyone, my name is Swati, and I'm one of the California AI Summit event organizers. I'm excited to educate all of you today on the potential of AI in healthcare, and I myself am particularly interested in finding tech-based solutions to medical issues.
All right, hello everyone, I'm Krish. I am one of the chapter leaders alongside Ashley for the California Girls Computing League chapter. And I'm really excited for this event because I love to hear about the speakers and their work with AI in healthcare. And I personally am really interested in using deep learning for specific healthcare problems.
All right, and I'm going to go ahead and run you all through the schedule for today. So after the opening remarks, the California chapter will give a brief introduction on AI, and we'll be giving you a summary of things like reinforcement learning, supervised and unsupervised learning. We'll talk about some applications of AI and also a little bit of how it relates to healthcare to give you a brief intro before you listen to our three speakers for today. So at 9:30, we will hear from our first keynote speaker, Dr. Enrico Santos, who is a data science leader at Bayer, and he will be talking about his journey in the field of AI and how AI is shaping the healthcare industry. From 10:30 to 10:50, we'll have a fun Kahoot game plan for everyone to test your knowledge on AI and the health sciences. After our break, we'll convene to hear from our first workshop leader, Dr. Christian Shelton. And Dr. Shelton is a professor of computer science at the University of California at Riverside. And he'll be talking about machine learning in pediatric intensive care units. We'll then have a lunch break, after which we'll hear from Sarah Gerke, assistant professor of law at Penn State, about ethical and legal challenges raised by AI in healthcare. Finally, at 1:35, we'll have the highly anticipated awards ceremony where we will be announcing the winners of the 2021 California AI Summit AI Ideathon competition. We were very excited to see the wonderful projects you all submitted, and we look forward to sharing the top projects with you. We will then have closing remarks, and if you won a prize in the AI Ideathon, we will have a quick meeting to discuss how you will claim your prize. So be sure to stay back if you are announced as one of the winners. By attending today's AI Summit, you are eligible to receive a certificate acknowledging your attendance and completion of the activities done here today. If you're interested in receiving a certificate, please email us at info@girlscomputingleague.org, which we will be adding in the chat after the AI Summit, and we will work on getting that email to you so you can receive your certification of completion for this event and all of its workshops. Additionally, everyone in attendance of the AI Summit today will be receiving our attendee prize package. This consists of an extended trial to Balsamiq Cloud, 1 free year of 1Password families, 1 free month of REPL.IT hacker plan, and a 20% discount code for ebooks. And these ebooks are related to STEM, comp sci, and I highly recommend you take advantage of these opportunities. So we're going to move on to our intro to AI talk. So I'm going to be leading this talk, and I want to ask you, what do you see in this image? You may recognize this as a CAPTCHA, and normally when you log into websites, you think, why are they asking me this? And the reason why is because on these websites, they don't want random computers to be logging in and trying to spam their accounts and try and like send random messages if they aren't a real person. So this is like a, are you a human being test? And essentially you may think, well, obviously a computer could be trained to learn that. And you're absolutely right. Computers can be trained to understand many things. So I have 3 examples up for you here. You'll notice the dog example. This is a very classic example with the dog versus cat classification. So artificial intelligence can be trained on thousands of images. And what it will do is go, okay, let me look at this image of a dog and let me look and see, maybe it has a longer snout or maybe it has larger paws, and that's what makes it a dog. And basically the robot will look for these types of factors in the image to try and classify whether it's a dog, cat, or other animal. It could be rabbit, bunny, etc. And after giving the computer so many images, it will be able to understand, yes, I know after looking at all of these different samples that that must be a dog. So this could also be applied to other complex scenarios, much more complicated than just identifying animals. We've seen artificial intelligence in sentiment analysis, where people try to gauge how people feel on a topic by, let's say, analyzing tweets, or they'll try and look for keywords in text, and the machine will go, well, I know when they're using the word hate, they're most likely having a very negative reaction. And you can train your machine learning models to understand how certain emotions may come about in human feelings. Although it doesn't directly understand, you can give it all these samples so it can act like a human. And this is the great part about AI, that it doesn't necessarily need to have all the complexities of human emotion, but you can attempt to teach it through giving it many, many samples and huge databases. So another example, which is more so related to healthcare, is that recently there's been a huge push for AI in healthcare. And for example, this image talks about how there's been mask identification. And this has been used in public settings, being that especially when quarantine was happening and mask mandates were extremely frequent, there were machine learning models that could identify whether someone's wearing a mask or not, or even if someone's 6 feet apart from another person in the area. And this was super beneficial for identifying when a person was abiding by COVID regulations. And this could be used in AI in healthcare, and healthcare could also be applied to anything in medicine. Think it could be organic chemistry, it could be biology, it could be disease research, cancer research. And there's just so many possibilities for AI, as long as you take the time to write the programs and develop strong databases with plenty of research. And you may be asking, well, how does a machine even make decisions in the first place? So think of the machine learning models as a web of neurons. When you think as a little pattern. It's kind of like each one sparks and then it goes to the next one in your brain. And then you go, okay, well, let's say we're thinking of the image of the dog. I see that there are floppy ears. And then those neurons fire and you go, well, I know this must be a dog because it also has a long snout. Well, this is what's happening in the machine. So the machine learning model is able to classify when it sees certain factors. So in this image, you'll notice there's an input layer. And let's say it sees floppy ears. And then it'll go to the next neuron and it'll go, okay, so based on seeing that was floppy ears, let me look for another trait. Let me look for maybe the big paws, and they'll go to this neuron. And then based on maybe I'll have another factor that it's looking for, and it allows for it to reach a single output of classification, whether it be dog, cat, etc. So essentially, machine learning models are being taught how to make decisions on their own and develop a neural network, an artificial neural network that is just like your brain. And something I really want to show you all is this demo. So there are many AI demos online that you can see. Something very exciting about this is that this is all live. So let me show you a quick one that I thought was really funny. So here's a lyrics generator. And essentially this generator was trained on thousands of lyrics. It was trained on many songs that probably are classics, pop songs, etc. And let's take a look at this. Sadly, I'm not going to sing this to you today. I'm sure you guys were looking forward to that. But basically, you'll notice it picks up on certain keywords that you may see in songs like a lot. We have kid repeated a lot, and it seems like this AI has understood that there are themes in songs, so it tries to repeat things. And normally in songs, you'll see repetition of the same line over and over and over again. And that's just awesome seeing that the machine learning model recognizes this. And the machine learning model is like, ah, yes, I know that when a singer is creating a song, they may repeat themselves a lot, and how a chorus is different from the verses. And by giving a machine learning model thousands of songs, it gives the AI the opportunity to think, well, what would another example be of lyrics that I haven't even seen before? So it's like asking a child to write its own song after you gave it a bunch of songs. And basically, I like to think of machine learning models as your own baby. It's basically being trained on whatever you give it, and then it tries to repeat whatever you're doing. And another demo I thought was very exciting was AI paintings. I've always thought these were very cool because these are all original, although this one looks more like a jumbled mess. You could see where it attempted to make out people's figures. Let's generate another painting. So essentially, this may be an image of war. I'm not sure exactly where the paintings are found from, but they're just generally famous paintings that the machine learning model is referring to. So you'll notice in this painting, it pulled a lot of images of trees. And that just tells you that the machine learning model understands that, yes, there's normally like a lot of greenery at the bottom. There's a lot of greens, and this may represent a valley, although it doesn't directly understand that, yes, this is a valley, yes, this is a tree. It can attempt to create art based on paintings it's seen. So we'll see images of water. There were some pretty great ones that I had seen the other day where it can generate whole fields of trees. You see how it attempted to even generate the face. The fact that the machine learning model understood that there's normally two dark spots around this part in the oval that resemble eyes. It did a pretty well job capturing the glimmer in the eye. And that's just very exciting. And these models can get so much better if you give it many more samples to reference, so it can be like its own artist. And going beyond those examples, I want to go into how a machine learning model determines right from wrong. So when you're thinking about different problems, you always go, okay, so this is right and this is wrong, and that might be resembled by a 0 and a 1. Think of a machine learning model creating a bunch of different outputs and going, oh, that's right, that's wrong, that's right, that's wrong. And then after determining all of those different pathways, it's able to create weights. So weights is what's used by machine learning model to identify what is the correct path, to understand what this image is, what this text means, and so forth. And along with that weight is also accompanied by bias. So a machine learning model may have not quite proper identification. It will be biased due to the samples that you give it. So it may, let's say you asked a machine learning model to identify cats and dogs, and then you don't give it any cats. It's going to have a lot of trouble identifying which ones are the cats because it only knows what a dog looks like. So you have to consider that there's more bias when you don't give your machine learning models many options to look at. It's like giving it a study guide to practice before you test it with a bunch of different sample images. And this is something that I touched on a little bit before, but ML models are only as good as their data. So I'd like to think of ML models as initially ignorant, and then as you teach them the way of how to understand a certain concept, machine learning models can learn to interpret new things, even if it hasn't been introduced to a certain sample before. Based on what it's seen, it can identify what this new subject is. And that's what I think is so exciting about machine learning models, just that it can take what it's seen in the past and then apply it to future contexts. It's like a human. And to give you a breakdown of 3 different sectors of machine learning, there's supervised, unsupervised, and reinforcement. So I'm going to start by going into supervised. So in this sample, you'll notice that the input is 3 apples. So you tell the model that, okay, here's 3 apples, and I'm going to tell you that these are all red apples. And then the machine learning model later receives an input of another red apple. Based on those 3 it saw in the past, it can go, okay, well, I know those 3 were red apples. This one looks quite similar. It has the green stem, it has the shine to it, the red color. Then I know that this has to be an apple. And that's essentially how supervised learning works in a nutshell. Just that it can take labeled inputs that you had given the computer and then go, okay, based on that, I know that this this new image I've received is for sure an apple, but that is also, remember, accompanied by a little bit of bias. It might not be able to perfectly identify an apple, but it would probably do pretty well in this sample. And then another example of AI is unsupervised learning. So think of this as I give you a set of 2 groups. I give you images of cats and I give you images of dogs. And I tell you, I'm not going to tell you what this actually is, whether this one's a cat or that one's a dog. I want you to figure it out. So the machine learning model will go, okay, well, I know this image of a dog looks quite different compared to this image of a cat. And it will attempt to cluster them and go, okay, well, I know this image looks like that one, and then I know that image looks like that one, and it'll separate them into groups. And then when it sees a new image, let's say we give it an image of another dog, it'll go, okay, that was most like this cluster of dogs. And although it doesn't specifically know that that's all dogs, it can identify and section them into groups to categorize them efficiently. And this is different from supervised learning because you're not actually giving the model specific labels. And so that's an example of how a machine can be unsupervised or doesn't. Unsupervised basically means not needing labels, and it will find patterns. And lastly, I want to go over reinforcement learning. So think of this as the Pac-Man game. It's basically where a machine learning model will take an action and it'll go, okay, let me test this out. Let me test this route out. And then it'll go through your environment, and then it will attempt to see whether it was right or wrong in the end. And it will be rewarded if it took the right path. So if it attempts to classify an image of a dog, we're going back to the cat dog example again, classify an image of a dog, and let's say it was wrong, it would put that was incorrect. So therefore I mustn't repeat that same process again to try and classify that dog that way. Those weights weren't right. So this machine learning model, it's basically a form of trial and error. And that's how ML can be trained to understand images without needing specific labels set beforehand, but it can identify whether it took the right process based on whether you tell it's right or wrong in the end. And as a breakdown, I just want to emphasize no model is perfect. Bias is extremely prevalent in so many machine learning models, and that you always need large data sets, and that ML can be applied to many fields. Today, we focus on AI in healthcare. AI in healthcare is a super big topic that's been rising recently, especially with the pandemic and so forth. We've had so much innovation in this field, and machine learning can be applied, as I mentioned like previously, to doctors' jobs. We've seen the autonomous robots that are even in restaurants or that you can see in the hospitals. And I've just thought all of this is very exciting. So that's what topic we'll be highlighting today. And our speakers will be elaborating on the connection between ML and healthcare today. Okay, so I want to start by going over Enrico Santos's speech. Let me see, if Yashu could introduce Enrico.
Yep, thank you, Ashley, for the wonderful presentation on the basics of AI. And on that note, it's my pleasure to introduce Dr. Enrico Santos. So Dr. Enrico Santos is a data scientist, leader, and trainer. After obtaining his PhD at the Chinese and Bilingual Studies Department at the Hong Kong Polytechnic University, he worked in several academic institutions, including CSAIL and MIT, in the group of Regina Barzilay. Enrico has published over 50 papers on topics related to the application of artificial intelligence to precision medicine, epidemiology, oncology, and cardiology. His work includes research on natural language processing approaches from automatic fake news detection and sentiment analysis. Enrico collaborated on the creation of the prayer, a mouth-shaped robot that produces original prayers, and it was exhibited at the Centre Pompidou of Paris. He's also the first author of Fact Sheet about artificial intelligence for the American Congress, and in 2019 he was invited as a speaker at the Record Management Office of the White House. Please welcome Enrico Santos. Dr. Enrico Santos, I'll hand it over to you. Take it away.
Thanks a lot, Yashu, and thanks, Ashley, for the nice introduction in machine learning. I'm currently unable to share my screen. Can you give me the right? In a while, I have to say, I posted a survey in the chat for the students that are present. The survey is mostly about to understand the audience that is there. So if you guys can fill it in a while, it would be amazing. It's gonna take just 2 minutes. There we go. Okay. Maybe I wait a second if I see that some responses arrive. Otherwise, I can start with the presentation. I see a few of them are already writing. So thanks in a while for the nice introduction to artificial intelligence. Okay, there are some shapes and then some numbers here. So most of people seems to be in the age between 14 and 16 so far. I see the number also is growing between 17 and 21. Your position are mostly into high school students, from what I can see from the survey. Computing, many people would like to do programming, data scientist, innovation on AI, and journaling somebody. And I see there is some kind of familiarity with artificial intelligence topics. And there's some familiarity with medicine and pharma, and that's it. Okay, for the moment I received 12 answers, so these are the 12 answers I received, maybe I start with the talk. Thank you. So today I'd like to start this talk a little bit with a funny point, which is this fish, right? And there is a fish in my life that actually changed my life. I will tell you why it happened, when it happened at the end of this talk. But in a while, let me talk a little bit about how artificial intelligence is transforming the healthcare. So the population grew pretty steadily in 1900. Until 1700, the population was growing at a low rate because there was very high infant mortality. But when hygiene improved and the healthcare in general situation improved in 1900, the population grew quite significantly. It quadrupled in 100 years. And as of today, the fertility rate is lowering consistently. So what this means is that we have reached the maximum level of population in most of the developed countries. And we are reaching what is called a plateau. So in a plateau, what happens is that the number of elder people, you can see this from this chart, the number of elder people will become dominant on compared to the number of younger people. So for the first time in 2018, the population above 64 was more than the population below 5 years old. So under 5 years old. So this is a very significant problem, and I'll tell you in a few seconds why. So what this happened like in the worldwide population, but in the developed countries, this happened in different times for each developed countries. For example, in the United States, it happened in 1966, in Spain in 1970, in South Korea, it happened in 2000. There are some countries that will see this plateau coming very soon. In India, for example, 2028, in South Africa, 2036, and Nigeria, 2087. So why is this important? Because this plateau corresponds to a growth of healthcare services usage. So it has been estimated that a person older than 64 uses 3 times the services that an adult uses, and 5 times the services that a child uses. This means that healthcare needs to scale to cover the needs that are happening. And scaling means more expenditure. And you can see this chart representing the expenditure in different countries. You notice that the youngest countries like China and India have only 4% expenditure in healthcare, 4% that is going towards 6% very soon. Italy, which is already a kind of old country, is going towards 10%, while the United States, where the sector is half private, is mostly private actually, is even above 17%. If you make a calculation in the United States, of course these numbers are referred to the GDP. If you make a calculation for the United States, it means that every citizen spends about 10,000 on average, 10,000 US dollars per year for healthcare services. And this is going to become even more in the next years. Of course, the COVID pandemic hasn't helped at all. It actually made this trend more pronounced and actually more worrisome in a certain sense. Another way to look at these costs is to compare them with the education. So what is very interesting is that in the majority of the countries, the costs of healthcare amount to 3 times the cost of education. You can imagine that how this is actually a problem, right? You could spend to educate your students, your younger part of the population to produce more, to be healthier and so on. Instead, you have to spend to maintain the elder people. and so on, the people in need. So let's see this. This is the major need for a change of paradigm in the healthcare system. As it is today, we have seen that it failed multiple times also in the most developed countries. I'm from Italy, and during the COVID pandemic, the healthcare system, which is very good, was in big troubles. It was in big troubles in the US, and it was in big troubles in any other country. That's the reason why there were policies to like lockdowns, to forbid people to go out, because those policies were meant to reduce the number of infected people so that the healthcare system could actually work properly on those that were infected by chance. This is, of course, unsustainable. We cannot live another pandemic as we lived the COVID-19 one. But on top of this need, there are also some other drivers, and now I'm going to speak about them. One is about the exponentiality of the technology, the exponential growth of the technology. And the other one is the availability, finally, of big data. Looking at the exponentiality, I refer to the fact that every certain period, every given period, the capacity, the performance of the machines and the technology doubles. And with doubling, the cost of the same technologies halves. So you have much stronger technology and you have reduced costs. From the technological perspective, what happens is that having a lot of technology available at lower cost, you can apply the same technology, the same new technology, to problems that were before out of reach. So if before they used certain devices that were very slow only for a specific healthcare application, now that these devices are very fast, not only they can be used much more and do more scans, more whatever we want to think about the device, but also they can be applied to new uses and to new types of diagnosis and so on. This is a clear example of this case. If you look at the CT scans, in the CT scans, if you look at these two charts here, on the left side, you see the number of pixels per second in between 1971 and 2015. You see how this growth was exponential. The number of pixels that these machines were able to capture per second has grew quite a lot. So the quality of the image. If you look on the right side, you see the speed. So in 1970, doing a scan took over 100 seconds. Now it takes 0.1 second. So we're talking about another important factor of this technological explosion. And what was the driver of this change? Well, there was the demand for a better image quality, because doctors were unable to diagnose anything in the first images. They were unclear. There was the need of increasing the speed of execution so that they could scan more people. And there was a new demand for new applications of the scans. And on top of this, also there was the need of safety. There are several studies that study the source of ionizing radiation in the US population in 2006. And 50% of those ionizing radiation were coming from artificial devices, and 50% of these devices were CT scans. So you can imagine all these drivers were pushing for development in this technology. Another very important technology, which today we hear very often, but actually until 20 years ago was something impressive and very expensive, is the human genome sequencing. Until 2020, the cost of sequencing the human genome was about 100 million of US dollars for only performing it one time. As of today, the human genome sequencing dropped to $1,000 in 2019. And probably now that we are in 2021, it's even cheaper. So this tells us how these technologies are actually making it possible to learn more about ourselves, about our health, about our genetic features, and so also to they give us a mean to study it and to utilize all these studies to predict. But we're gonna go back to that. This is a quote by Topol, and it says that the merger of the branches of information technology and biology will positively influence the future of medicine. The extraordinarily powerful set of information technology offers the ability to understand, and here is important, I have highlighted it, understand from the medical point of view the uniqueness of each individual and the guarantee of providing healthcare in a much more rational, efficient, and tailored way. So rational, because we can actually look at the data both from the individual perspective and the population perspective. So always remember that in medicine there are these two perspectives. We want to take care of the individual, but we can look at other individuals with similar characteristics to understand exactly what's happening on a single individual. So this, and efficient in terms of speed, in terms of costs, resources savings, and efficacy. And the other point that I mentioned before was the big data. So now we move towards that side. According to the IDC, as of today, in the world, we have produced about 44 zettabytes of data. Or now, you can see on the chart in the left the exponential growth of data that were generated by humans in internet, in the digital universe. This growth is continuing at a rate of 70% per year, which means that, for example, between 2020 and 21, it will grow another 6.8 zettabytes, and then you can imagine the following year will be even more than that. So how to represent that much data? So if you think that you want to store this data on tablets like iPad or Samsung, whatever it is, you store it in them, you will have enough tablets to do 6.6 piles of tablets between the Earth and the Moon. So this is just to give you a visual idea of the amount of data that we have generated so far. And this data is characterized by 3 V's: velocity, volume, and variety. Velocity, in the sense that this data can be generated, for example, once for all, or it can be generated periodically, or it can be generated near real time, or actually real time, so continuously. Imagine a camera in a city that look at the traffic, is generating data in real time. Then there is the size, the volume of the data. Some time ago, megabytes, when I was a kid, 1 megabyte was already something huge. And now we are talking without any problem of gigabytes and terabytes, right? And if we look at the big picture, there are petabytes, there are zettabytes. The type of data, also the variety. So there are tables, there are databases, there are pictures, there are videos, there are social media posts, and so on. So the number and the typologies of data is growing every time. And also the number of sources of data. Until some years ago, data was generated by humans for other humans. Now data is being generated for humans to machine, and also from machine to machine. For example, if you think about the wearables that are collecting our heartbeat, our steps, and so on. And all this data is very crucial in the healthcare domain because it allows you to diagnose something very quickly, or to check the health of a patient in real time. And moving towards a little bit more towards the applications in the healthcare domain. As of today, 80% of the data that is being created is unstructured and untapped after the creation. So there is a paradox here. If you look at the chart on the left side, you see that the available data is growing exponentially, but what we are able to do with this available data is growing linearly. And so there is a big gap, which is the gap between available data and the ability of using it. The reason is that in 60, for example, 65% of the visits, the doctors are unable to read all the patient medical history. So they rely on what the patient says, but the patient is not an expert. So sometimes this brings to errors. And later I'll show you how many these errors are. We don't know, but they are actually many and they are dangerous. We are talking about millions and millions of pieces of information about the socioeconomic status of the patient, the medical history, the diagnosis, the treatments, the genetic information of the patient. So imagine if we were able to actually utilize all this information to extract insights and make prediction, possibly on the population level, so all the patients with certain characteristics, but also on the individual level, because we want to recognize also the individual characteristics. And we cannot do that because as of today, we are still using an outdated technology, which is humans. Humans are slow in reading text. An average reader can read 200 words per minute with an understanding of 60%. A very excellent reader can read up to 700 words per minute with 85% of understanding. So to scale to the real large amount of data that we are creating every single day, we definitely need some help. And this help may come only from artificial intelligence and particularly from natural language processing. Natural language processing can help to extract information, organize it in knowledge bases, and finally using it for tasks. It is the path from data to information to knowledge to action. And that's where we are actually investing. Actually, before was talking about how artificial intelligence works. I will speak a little bit about it too, with a minor focus on the natural language processing. There are two concepts that you have to keep in your mind: representations and similarity. Representation tend to try to capture some patterns. Similarity try to capture how similar the patterns are. So let's get into some specific examples. If you have a representation if you look at the image in the top left here, you have you can see several vectors. The vectors is the most typical mean for representing data, whichever data you want. So if it's textual data, it's representing one vector where the numbers are somehow summarizing the characteristics of that piece of data, whether it's a text or it's an image. Generally, images are represented in matrices, which are simply two-dimension vectors, or they can be three-dimension vectors if they are colored ones. What happens is that once you have this representation, numerical representation, you can project this representation in a graph and see how close these representations are to each other. You see this in the images below, right? And you can calculate the distance. And the distance, if the representations are close to each other, then it means there is low distance. It means they are similar to each other. If they are far apart, then it means they are different. Moving towards the words in this slide, you see that, for example, you have school and college in the first picture in the top left are very close to each other. You see that educational and education are close to each other. You see that teach and learning are close to each other. But for example, degree and master or degree and teach are far apart. So this tells you that these words there are some words that are more similar than others. One important property of this space, which are called vector spaces, is that the distance and times keeps some meaning, such that if you have two words like king and queen, and you have two other words, man and woman, they maintain a similar distance from each other. And this allows you to do some simple mathematics. So you do king, you subtract man from king, you add woman, and what happens is that the representation you will have is approximately the one of queen. This is very interesting because it allows you to perform some entailment. And entailment is at the base of every reasoning that we perform. As much as you can do it with king and queen, you can do that also with capitals of the countries. So you get Spain, you subtract Madrid from Spain, you add Rome, and what you're gonna get? You're gonna get Italy. And that's how it works in the vector spaces. And if it works on the words, if you have very good representations of the sentence, you can do exactly the same thing with the sentences. Okay? But how is this possible? It is possible thanks to these representations. And this is what Ashley was mentioning when she was talking about the unsupervised learning. Unsupervised learning is based on looking at the distances between representations. Instead, if you move towards supervised learning, what you try to do is to project all the representations of multiple items and try, for example, to classify them according to some classes. These classes can be whether it's a dog or a cat, whether the person is sick or is not, and so on. It's just depends only from the type of data that you're utilizing, the goal of the machine learning method. But all the machine learning methods learn in thanks to some annotated data in a trial and error approach. What they do is they have, as Ashley was mentioning, a network of neurons that gets adapted during the training process with their weights in order to return the output that reduce what is called the loss. If you look here on the top left side, you see some mountains. Those mountains are called the cost function of the machine learning method. So when the machine learning method is not trained, it makes a lot of mistakes, and the cost stays on top of those mountains where it's red. So the goal of the machine learning method at a certain point is going down from this mountain to reduce the cost and get down to where is blue. When it does that, when the system does that by making errors, so it makes an error and it knows that with that error is not going down at all. So it tries again. And when it succeeds, it knows it can go down a little bit. And it keeps doing that multiple times until it reaches the blue side, the blue part of those mountains. Similarly, if you look in the bottom left, there is this chart with the red and blue dots. While you see there is this line. Well, this line is totally in the wrong place currently in this image. But as soon as the error goes down, this line is going to go between the red and the blue dots, and it will separate them. And at that point, the system is trained and will be able, given new data, to say whether this new data is red or blue. So that's how machine learning methods work. The very interesting thing is that they evolved very fast in the last 10 years. Until 2013, mostly the methods that were utilized were the classical machine learning methods, where humans were creating the representation. And that's what you see in the top right image. There were humans that tried to encode whatever they wanted to represent with some features. So, for example, you want to represent a car. You say it has 4 wheels, it has 4 windows, it has 1 engine, and so on. And that's going to be a representation, a vector representation of the car. And then the system was trained on this type of representation. Instead, now, the system can learn this representation automatically thanks to deep learning, which is inspired to the biological neurons, as Ashley mentioned before. So getting into the healthcare domain, why is this important? It is important because as of today, all the clinical decisions are taken on the base of 3% of the population that participated in clinical trials. So basically, we are trying to generalize what we have learned on only the 3% of people to the rest of the population, to the remaining 97%. You can imagine this is very bad. And indeed, it brings to a lot of deaths. So as of today, before I was talking about the medical errors. As of today, if you look at these 3 bars, the first one is cardiovascular diseases. It causes only in the US about 650,000 deaths. The cancer causes about 600,000 deaths. Medical errors in the US only cause 250,000 deaths. So you can imagine if you would be able to utilize this data much better and to have more data about every single patient rather than only this 3%, how this number would be different. The reason is that what we do is that we look at the diseases, we look at the healthcare problems as if we look at the left image here. So we have very few data points, which is like we have very few pixels basically to understand what that specific disease look like. If we had a high resolution image like the one on the right side, we could definitely understand much more about the diseases and about the problems at hand. This is the reason that motivated me and some other colleagues while I was in MIT to extract information automatically from pathology reports and turn this unstructured information into structured information. What it means? Unstructured information is free text produced from a human by a human to another human. And this type of information is understandable only by humans. And for this reason, you cannot do any statistics on this kind of information. So how to improve that? Well, use artificial intelligence to turn it into a table. The table can be utilized to perform searches. For example, the doctor may check, I want all the people that have invasive lobular carcinoma and positive lymph nodes. That could be a query. And then it's going to get all the list of people with that specific characteristics, and they can check what kind of diagnosis they have, what kind of life they had, expectancy of life they had, and so on. And so they can take decisions based on all these pieces of information. To perform this, we utilize a convolutional neural network, which took in input the report. It turned the report into embeddings. You can see here, as you remember from before, I said every word is represented by an embedding, by a vector. You can see the surgical as its own vector, pathology as its own vector, and so on. So you have a matrix, actually, that represents the full text, where every row is one word. And then you run on top of these several filters, which are adapted by the machine learning method on some annotated text, where you have already extracted and annotated all the important information. And then there is a max over time pooling layer that with a soft max allows you to predict whether something is present or absent. And you can just, after you train the system on some thousands of annotated reports, you can perform this on many others in at a very fast pace. We indeed did that, and we had a system that worked at 96% accuracy. We could create a database for 90,000 patients with 160,000 reports in a couple of days after the system was ready and running. This helped us to do something very important. Until then, most of the studies, even in the top journals, were made on top of 336 cases, 674 cases. But with our system, we were able to make a study on top of 6,000 people. And so you can imagine if you look back at the Mona Lisa, our studies have definitely much more pixels than the studies that were published before. We adapted this for multiple types of cancers: breast cancer, prostate cancers, lung cancers, pancreas cancer, and so on. Another application of AI in the healthcare domain is for the CRT, cardiovascular resynchronization therapy. It's a heart surgery, and it's very risky and very expensive surgery. And only 2/3 of the patients that undergo the surgery generally benefit of it. There is 1/3 of patients that don't benefit of it, and a subgroup of them that even die because of the complications of the surgery. So in this case, imagine how crucial it is to understand who is going to benefit from this surgery before doing the surgery. So we want to send to the operational room only people that we are certain will benefit of it. We started collecting data, structured and unstructured, such as demographic information, gender, age, past health services, utilization, bill codes, encounter information, laboratory values, medication, clinical information, and even the EHR notes. We tried to train to get all this information input represented into vectors, into matrices, as we said before, and then projected into our historical information. So we knew we had a data set where we knew for thousands of people whether they survived or not. And we used this as a data set for training the model. The results were interesting. We got a precision of 79%, 26% of recall, and you can see that in the image on the right side. So if you look at the top, we have 100 patients, and you have that 41 of these 100 patients didn't benefit from the surgery. Our system was able to identify 11 of these 41. You see the pink ones that you see in the bottom. Our system was able to say, those pink ones, please don't send them to the operatory room because to the surgery room, because they are not going to benefit of it. And finally, the last project that was developed together with the University of Udine and University of Pisa and Hong Kong Polytechnic University. It's a system that was made at the beginning of this year when there was a lot of hesitancy about getting vaccinated. What we wanted to know was what is the opinion that people have about the vaccines? What scares them? Because once you know what scares them, then you can somehow try to solve the problem at the root. And we created this system, which is a website which is publicly accessible. If you're interested, I can send you later the links. And this system has several modules that are represented in this image. So it collects tweets from Twitter that talk about the vaccines. It checks the localization of the tweet, it checks the hashtags of the tweet, it checks which sources of information the tweet mentions, it checks the sentiment, whether it's positive or negative, and finally it checks whether the person is speaking about side effects, so adverse events. Because one of the reasons why people doesn't trust the vaccines is because sometimes they cause side effects. So we wanted to see which side effects are most worrisome for people. So here you see the localization module, which is represented into a map. The map at the time was working only for English text, so it makes sense that only the Anglophone countries are darker, while the others tend to be a little bit lighter. As of today, we have implemented also for other languages. You see here the sources of information. What we found is that the most tweets, the most cited links were generally reliable newspaper or reliable media, but you have a huge amount of unreliable media that are cited less times. So that's where we actually identified the possibility of of intervening. And the other issue was the side effects. Every year, dozens of drugs are entering the market after they are tested in clinical trials. But clinical trials are not always able to capture all the possible side effects because they are too small sometimes. And side effects are the cause of 5 to 8% of the hospitalizations in the US. And they are growing at an enormous speed. Between 2008 to 2017, the FDA received over 10 million of adverse events reports, and 5 million of which were severe, 1 million of which were related to the death of the patient. So you can imagine how big this problem is. And that's why we started extracting every side effect that was mentioned in those tweets. And you can see them into this word cloud, where the bigger side effects are those that are mentioned more often, and the smaller ones are mentioned less. And if you click on one of those, for example, on facial paralysis, you can see which tweets are talking about it, and whether the tweets are positive or negative. So they are green if they're positive, red if they're negative, they are gray if they are neutral. We also aggregated all this information to see which vaccine has the most citations about a specific side effect. And you see that, for example, Pfizer is very highly correlated with allergic reaction, while AstraZeneca with headache, and so on. This led us to a publication where we also all this work was somehow included in a publication this year about how to utilize AI for precision medicine, also in particular for COVID-19, also looking at the strategic areas for research and development. This work was done, of course, with many colleagues like Nicola Marino, who I have to thank also for the support in building the slides. To close a little bit this overview of AI in healthcare, let me say that the current market of natural language processing is about 1.5 billion in the US, and is likely to grow at an annual growth rate of 20% in the next years, reaching 3.7 billion. So it's a market that is growing a lot. The US is ahead of everyone else. Europe is following. The Asian countries are following too. So it's a market that needs a lot of work, a lot of brains, and hopefully you're going to be supporting this growth in the next years. And here I will close my presentation with the story of the fish. This is a personal story, and I knew that I was speaking with young people, and I knew that when I was young, I didn't have very clear my path. So I was asking myself what I want to become when I grow up. And one thing that I wanted to become was a cook. I wanted to become a cook, so I went to a cook school in high school to somehow follow a little bit the career that some of my relatives had successfully. And I started studying for that. And then one day I was given a fish and I was asked to gut the fish. And I was unable to do that because I was also a little bit animalist. And when I was unable to do that, I actually realized, is this really what I want, or it is just following the path that my relatives have already opened before me? And that's the moment in which I realized that I could create a new story in my family, something that nobody had done before, and it could have been only mine. So this is just to tell you that you can do obviously the same. And so let whatever inspires you, whether it's a fish or something else, move it towards your final goals. Thanks a lot. Thanks everyone. Happy to talk with you, and I'm available for any question.
Thank you, Dr. Santos, for the great presentation, and I am sure our participants enjoyed the presentation a lot. We do have some questions. I will read them out. Yeah, let me know if you can't hear me. Yeah. So, Gaurav asked if is it due to expenditures that in a few nations the cost of getting a surgery is expensive?
Sorry, I don't understand. I didn't understand.
He's asking if expenditures is the reason why in a few nations the cost of getting a surgery is expensive.
Yeah, the expenditure is okay. I'm seeing the questions now. No, it's not the reason. It's not only the reason. It can be the reason, but it's not only that. The reason is that in the developed countries, people has the lack of using healthcare much more. Of course, if you live in an underdeveloped country, you only use the healthcare, which generally is not good, only when you really need it, because you're like in a very bad condition. In the developed country, you use healthcare for many other things, also for a cold or for whatever it takes you. So this drives the costs. Elder people tend to use it much more compared to adults and children. So that's the reason why having an older population will impact more the costs in the healthcare systems.
Yeah, thank you for that. And our next question is asking what the best course is to pursue healthcare advancement and innovation.
As a course, you mean like online? You mean like university? It's hard to, sorry?
Yeah, I think they mean university-wise.
Okay, so university, I think there are several ways to get there, and depends a little bit on your personality and what you want to do. There's people that are very great contributors from the development perspective, so the implementation perspective of these algorithms. There are people that are more into the business perspective, so they want to understand the healthcare business, so they go and they pursue something that is more related to the business, and they keep a very attentive eye on the technologies. So what I always suggest is look at yourself, what you like, and depending on what you like, take one of those ways. There are many universities that are offering classes into that. If you want to know more, I can also check. If you're interested in, at a certain point when you're gonna go to the university, you can let me know. But the important thing is that you pick the branch that is better for you, for your personality. I tell you so because when I enter in the AI world, I enter from a very different perspective compared to my colleagues, which were engineers. I was a computational linguist. Computational linguists are different because my training was a soft training, was on linguistics. It was not on computing. It was in linguistics with a little bit of computing. And this allowed me to build some skills that they didn't have. I was much more oriented towards communicating, leading, understanding the conceptual part rather than actually writing code. But there's other people that are more engineers in the way they are, and they can write code and they are better in that side.
Right, yeah. I think if you had a follow-up question for that, whoever asked that question, you can ask that. Yeah. Gaurav also asked another question, and he asked if you can identify, if AI can identify identical twins individually, even if their images are pixelated.
That's very interesting. So AI learns patterns. If you train the system on pixelated images, and the two images are not exactly identical, so there are some, let's say, low quality images that are pixelated, but still you have some differences between one and another. Definitely the AI system, yeah, can identify them. It depends, as Ashley was mentioning before, on the training that you give to the machine. If the machine is trained on recognizing humans versus dogs, and then you ask to the machine, is this human different from that human? Maybe the machine is not able. But if you train the system to recognize one human from another, then that machine should be able to distinguish even identical twins.
Thank you. Priyansha asked about your views on the IoT system along with AI. She thinks that it could be helpful in healthcare, but she wanted to know your views on it.
Yes, absolutely. So I'm reading the email because Yeshu, your audio is a little bit hard to follow. So absolutely, yeah, that's a very good point. Yes, IoT is crucial. Is a crucial development in AI. All these devices that are collecting data of any type in the wearables, in our watches, in our cars, in our clothes, even. They're gonna be crucial to send this information to a machine learning system that can be utilized this information to extract signals, to get insights about this information. Also remember the distinction between individual and population. If you collect more information about the population, you automatically will recognize the individuals, because you automatically will see where you and me differ from each other, whether it's the age, whether it's something else, because you can contrast my information and yours. So yes, IoT is crucial also for that.
Priyansha had another question. She said that she's in Bachelor of Technology, right, in Engineering Information Tech, and she's asking what courses she should take in order to engage in medical sciences.
Yeah, that honestly, I'm not sure. I don't feel I can give a clear answer to that. I don't have a medical background, so I reached this AI branch from linguistics. So I was interested in language, I was interested in text, how to extract information from text, how to elaborate this information such that we actually can make the doctors able to find queries and so on, rather than medical information. So honestly, unfortunately I cannot help on this.
Yeah, that makes sense. Yeah, so I think it also depends on where you're going to and what you're interested in to take the courses for that. We have another question. So someone asked if we can make 3D devices that can make decisions like the human brain.
So we're using India. So the question is whether they're using India and how can we improve their effectiveness. So the effectiveness can be improved, for example, by collecting data about whether the reaction of the immune system to the vaccine, and this is being done. You can make experiments by changing a little bit the RNA of the COVID vaccine and see what differences there are in the immune system, in the reaction of the immune system. This is one way. And again, this way you can do, of course, in the clinical trials with all the safety requirements that are requested in that sense. The other way is that you look at the differences between the genetic characteristic of the people that are getting the vaccine, and you see how their reaction to how their immune system reaction change. So if you can basically compare between the reaction that I have, for example, the reaction that another person have, and you can see the differences in our genome, then maybe you can correlate our differences to certain types of reaction. Of course, you don't do this with 2 people. You need to do this with thousands and thousands of people. And that's the reason why you need AI, because you cannot do it very simply.
And our GCL California team also had some questions on your presentation that we'd like to hear more about. I know you talked a little bit about going forward with being a chef and talking about the scenario with the fish and deciding to choose a different career path. Was this a difficult process? And how did you navigate learning more about machine learning and CS in the professional industry?
Yeah. So thanks for the question. Yes, it was a difficult process. It was a very exciting process because the lack is that when you change your mind about something, you have a lot to learn. And when you have a lot to learn, it's a very nice trip that you are taking. My path was very peculiar. After desiring to become cook, I went to study literature and then linguistics. And then in linguistics, I discovered computational linguistics, which was exactly what brought me towards artificial intelligence and natural language processing. In this path, I think the most difficult year was when I went to MIT. So starting from a background as linguist, getting in MIT, where everyone is engineer, and these guys were writing equations on the walls of the lab. And I couldn't even understand those equations because that was not my profile, my training. That was a hard period. But it was also the period where I understood something very important that I'd like to pass over to you, which is like we are different. We have different training, we have different experiences in life, and we have different values. And those values are important. So when I reached MIT, MIT was doing a project with Bayer, my current company. I work currently for Bayer. And this project was not going well. Why? They didn't know. They didn't know why it was going well. The reason I tell you, and I discovered it myself, is because they were unable to communicate their results. They were unable to discuss with the management of Bayer in the way the management was satisfied. So they were engineers, very strong in the code, very amazing in the code, but they were not interacting in the right way with Bayer. So I got the responsibility of bringing this project to a conclusion, and I started being the middleman between Bayer and my colleagues that were developing whatever they were developing. And it worked. It worked. And it worked only and only because these guys were amazing code writers, and because I was able to turn whatever they were doing into some slides and present it to Bayer, or understanding the requests that Bayer was making to them and translating them in technical specs. And this gave me a role in MIT. That's why my contract was renewed. That's why other things happened. Without that, it would have never happened. So in that moment, I was not able to write the code that they were writing. I was unable to read the questions that they were writing. So I felt very out of the comfort zone, but I found my position there. And that's what always I suggest to you, to look at things from new perspectives, and you can get there. The reason why I'm working for Bayer is because Bayer was impressed with the work that we have done. And so after the project, they contacted me and they made a proposal. And again, if I would have been a very good programmer and very somehow unable to communicate my results, probably Bayer would have never approached me. So.
Yeah, and that's amazing. And I know as a professional in AI and healthcare now, I was wondering how, what you think are the biggest obstacles in AI and healthcare. I know you talked about how there's very small sample sizes, like 3% of the population for our databases. Can you elaborate more on this, or any crucial issues you feel like there are in AI and healthcare?
Yes, so there are many challenges. One of the challenges is that doctors, to write the notes, as of today, they spend over 55% of their working time. So doctors are actually not caring enough to the patient because they have to focus on those notes, writing those notes. And as I mentioned before, 65% of the times, these notes are never read anymore. So you have the paradox of spending a lot of time to write these notes and never read them anymore. And this is the reason why we are collecting a lot of data. But this data is like a library without humans inside, right? If you have a huge library, but you don't read any book in it, you're actually learning nothing out of it. So one of the challenges is like getting all this data, turn it into information and then into knowledge so that we can actually execute on that. So this one is one of the challenges. Other challenges are, of course, from bureaucratic perspective. There are regulators, there are a lot of issues with privacy. Of course, we are treating data about patients, so we need to be very careful about the privacy of patients. And this slowed down significantly the process of using machine learning and new tools on patient data. I don't want to enter in the ethical part of this. I want just to mention this as one of the difficulties that as a data scientist I have to face regularly. Other major problems is that doctors and managers don't speak the same language of data scientists. So you have these doctors that eventually think AI can solve every problem, but they do it naively. Or you have these doctors that are very diffident. They don't believe AI can solve anything at all. And so you end up trying to explain them what are actually the strengths and limitations, but the language that they speak with you and the language that you speak with them as data scientists sometimes is not very clear. That's why we need profiles that are somehow in between. And I really suggest for those people that have this kind of interest to go in between. So some medical learning and some technology learning, some business learning and some technology learning. Because otherwise we have people with very sectorial type of language and unable to understand the others. And data science today is going to be everywhere. Healthcare is only one of the biggest domains.
All right, thank you, Dr. Santos, for that amazing and inspiring inspiration. We really appreciate your time. Now we will be having a quick Kahoot game to test everyone's knowledge on basic AI concepts. So yeah, Dr. Santos, you're free to leave whenever you're ready. But yeah, thank you for your time.
Thank you very much, Chris. Thank you, Asley. And thanks everyone, Yashu. Bye-bye.
Thank you, bye-bye.
Thank you so much.
All right, so everyone should go to kahoot.it and join with this code. So go to kahoot.it and fill in this code, and we'll start in a couple of minutes once everyone joins. Okay, I'll give everyone a minute more and we'll start at 10:35. All right, we're gonna get started now. You can still join the Kahoot if you have this pin, so maybe just quickly take a screenshot if you're unable to join. Also put it in the chat. We're gonna start. And if you don't know these questions, that's perfectly fine. These are just questions about like the fundamentals of AI. So hopefully you can learn a thing or two from this Kahoot. All right, so we're kind of split on that. So generally classification regression will be supervised learning techniques. Okay, so this is clearly an example of bias because the AI system is wrongfully classifying Black people as gorillas, which is obviously morally wrong and just like messed up. So that can be like a major issue of AI systems that one of the speakers today is going to cover. This is just a fun trivia question. All right, most of you got that one right. All right, great. Most of you got that one right. All right, yeah, so these are all examples of pattern recognition. All right, so that's good. Most of you got this one right. So as Ashley and Dr. Santos had briefly covered in his presentation, unsupervised learning is essentially when you're kind of extrapolating patterns from just the data alone. So you don't have any labels or any truth available. You're just trying to make judgments based on the data. And one of the most common ways of doing unsupervised learning is through clustering the data. So usually when you hear clustering or you see clustering, it's usually related to unsupervised learning. Right, so yes, a classifier is essentially when you're trying to group, if you had like a ton of data points, you're trying to group them into separate categories. And while some of these answers could technically be right, they're not exactly right because a classifier is not really an algorithm. There's algorithms that are based on the idea of a classifier, but a classifier in itself is not an algorithm. So it's essentially just a function that is mapping input data to output. All right, yeah, so it's good most of you got this right. So naive Bayes is a classifier that is not that commonly used. Like nowadays, not many people use it, but if you don't have as much training data or you're trying to make it such that the model cannot be influenced by like correlations between features, that's kind of a case where you would use naive Bayes. But for the most part in the modern day, like for most problems, we don't really use naive Bayes because of the amount of data we have like access to. So yeah, these are all correct answers of kind of how the structure developing a model in machine learning works. So coding is kind of part of like developing the model. So that's why you would not really count model coding as a separate aspect or separate stage of constructing a model. So yeah, the first thing is you want to build the model, then you want to be able to like test it on different applications, then finally you want to be able to apply it on like the real world. This is just a general question. All right, so yeah, hopefully most of you got that one. The idea of AI is just to make machines or computers simulate our human intelligence. Another general question. All right, so yeah, this is the right answer because everything is autonomous and you're using a computer program to build it. It's not a manual program, so it's not a full like a list of conditionals that's like if I get this training data, then I'm going to do this. It's fully autonomous. All right, so hopefully you guys got this one right. So decision trees, neural networks, and k-nearest neighbor are all common machine learning models that you'll see as you get involved with AI. And I think both the previous presenters kind of briefly touched on some of these. All right, so something to keep in mind, not many people know that within AI, there's different types of AI. So there's artificial narrow intelligence, there's artificial general intelligence, and there's artificial super intelligence. So the difference between these is narrow intelligence is for like a specific task, like using AI for maybe diagnosing brain tumors. That would be an example of narrow intelligence because you're making a focus on one task. General intelligence would be something where you're making a where you're trying to simulate a human. So it's like creating a robot that's an AI pretty much. And there have been some companies that have tried to make this, but we're nowhere close to it being successful or actually simulating a human. It's basically an AI that can do a bunch of different tasks at one time, like maybe cooking, maybe like watching TV, just like a bunch of different tasks at once and like using AI to influence their decisions. So we've not been successful at this yet. And artificial super intelligence, we're nowhere near yet. That's creating a superhuman with AI. So the only one that we've really been successful with is artificial narrow intelligence. And this ANI for short, this is AGI, and this is ASI. You're going to hear those terms if you get more involved with AI. All right, so it's good that most of you got this one right. So again, the difference between supervised and unsupervised is for supervised learning, you're going to have labels. So let's say you had like a data set of images of like a cat. For supervised learning, it would actually tell you that this is a cat versus this is a dog. But for unsupervised learning, it would not specify those actual labels. So you would have to identify that yourself with the model. So that's the primary difference between those two. And some people might have chosen this, but this is just not correct because unsupervised learning does have its applications, and in some cases, it can perform better than just supervised learning. All right, so hopefully you guys knew that. So naive Bayes is fully based on statistics and probability. All right, yeah, so hopefully you guys got that. AIs are capable of pretty much doing any specific task that we give it. There are a few examples of things that AI can't do, but definitely creating, developing or identifying new molecules is something it can do. All right, so it's good most of you got that right. This is a pretty important question, so I'll quickly show you guys what it should look like, but this is pretty much AI. Sorry for my bad handwriting, and this is ML. So that's kind of what it looks like, and there's a bunch of other circles that AI also covers, but ML is the main one. All right. So last 3 questions here. Yeah, so this is an example of what inductive logic programming looks like. I'm going to be going through these questions a bit faster since we're a bit short on time. All right, so this one should be pretty simple, hopefully. These 3 are all related to healthcare. So the wording in this question might have been a bit ambiguous, but the main idea is that training set is kind of the data that your model is being based off on, and test set is what you test your model on to evaluate how good it is. Okay, that was it. Let's see the podium. So nice job. 3rd place. 2nd place. And congrats to A, who got 1st place, 15 out of 20. So yeah, that's pretty much it for the Kahoot.
For the 10-minute break, we are going to begin it right now. Thank you, Krish, for that fun game. I'll go ahead and set the timer right now, and I'll share my screen so you guys can keep track of where we are in the break. We're most likely going to set it for about 8 minutes to stay on schedule. So let me share my portion of the screen real quick. All right. Okay, so I'll set this for about 8 minutes. Okay. So I'll be checking back in with all of you, and go grab some water, any snacks. We'll be having a presentation after this, and I'm looking forward to seeing you all and hearing your questions.
Great. Welcome back, everyone. We hope you enjoyed your break. It is my great honor to introduce our first workshop of the day, led by Professor Sarah Jerke. She's an assistant professor of law at Penn State Dickinson Law. She previously served as a research fellow in medicine, AI, and law at the Petrie Flom Center for Health Law Policy, Biotechnology, and Bioethics at Harvard Law School for the project on precision medicine, AI, and the law, where she oversaw the day-to-day work of the center's component of this collaborative project, including conducting law, policy, and ethics research, drafting reports and recommendations, and coordinating the center's efforts with collaborators at the Center for Advanced Studies in Biomedical Innovation Law at the University of Copenhagen, as well as other partners. Before joining the Petrie Flom Center at Harvard Law School, Professor Jerke was the general manager of the Institute for German, European, and International Medical Law, Public Health Law, and Bioethics of the Universities of Heidelberg and Mannheim. I'll hand it over now to Professor Jerke.
Thank you so much. I'm going to share my screen and then we can directly start. So I hope you are able to see the screen now. Perfect. So thank you so much for the kind introduction. So I was thinking to talk a little bit today about some of the ethical and legal aspects of artificial intelligence in healthcare. And then we have also a few minutes for questions and answers. So I will first briefly explain what artificial intelligence is and give you also some examples of potential AIs in healthcare. And then I will focus on a discussion of some of the ethical and also legal aspects. And lastly, I will make some concluding remarks. So what is AI? So to date, there is no universal definition of AI, but the term is often used as an umbrella term to encompass several subsets. And in particular, its subset machine learning has become one of the most promising fields of computer science in recent years. And machine learning uses algorithms to detect patterns in data. And a subset of machine learning is deep learning, which identifies data patterns by employing artificial neural networks with lots of layers. So AI is really rapidly entering healthcare and may fundamentally change the way physicians practice medicine in the future. So the US Food and Drug Administration, the FDA, has already permitted marketing of over 160 AI-based medical devices. And in particular, health AI shows really great promise in medical imaging and disease diagnostics. So for example, this is IDXDR. It's a medical device that uses AI to detect more than a mild level of diabetic retinopathy in diabetic patients. And the peculiarity of the system is that it is considered autonomous, meaning that its decision does not need to be reviewed by the primary care physician. So since its marketing authorization in April 2018, IDXDR has been deployed in over 20 sites across the US. And according to one recent estimate, the global health AI market size is expected to increase more than 9-fold from 2020 to 2026 to $45.2 billion US. And in particular, tech giants such as Google, Microsoft, IBM are really key players in the health AI market. And the COVID-19 pandemic has only hastened the adoption of health AI. So in the context of health and research, it's really expected that AI will be increasingly applied in 4 areas. So the first is clinical application, such as imaging, diagnostics, and AI-assisted or autonomous robotic surgery. And then the second is patient consumer use, so such as health AI apps ranging from diet guidance to psychological advice to contact tracing apps, fitness trackers, and also chatbots. And then third, research and development process. So here we have the acceleration of the drug and vaccine discovery process, but also higher efficiency of clinical trials. And then fourth, workflow optimization, such as the reduction of costs and also the training of clinicians. So let us now shift to some of the ethical and also legal aspects. So as we have seen, AI holds great potential to transform healthcare for the better, but at the same time, it also raises ethical and legal challenges that stakeholders such as AI makers, healthcare providers, patients, ethicists, and regulators need to really be aware of and address in a collaborative effort as early as possible in the development process of these products. And there are in particular 4 relevant aspects that I will discuss in a moment. And that's informed consent, safety and effectiveness, liability, and data privacy. So let's start with informed consent to use. So health AI applications such as imaging, diagnostics, and surgery will really transform the patient-clinician relationship. But how will the use of a health AI actually interface with the principles of informed consent? So this is a pressing question that has not received enough attention in the ethical debate, even though informed consent will be one of the most immediate challenges in integrating AI into clinical practice. So there is really a need to examine under what circumstances, if at all, the principles of informed consent should be deployed in the clinical AI space. So to what extent do clinicians have a responsibility to educate the patient around the complexity of AI, including the form of machine learning used by the system, the kind of data inputs, and also the possibility of biases or other shortcomings in the data that is being used? Or under what circumstances must the clinician notify the patient that AI is being used at all? So these questions are especially challenging to answer in cases where the AI operates using black box algorithms. So where the software designed to assist clinicians does not explain how the input data is analyzed to reach its decision. And so this lack of knowledge might be worrisome, for medical professionals. To what extent, for example, do clinicians need to disclose that they cannot fully interpret the diagnosis or treatment recommendation by the AI? Health AI apps and chatbots are also increasingly being used, ranging from diet guidance to the help to improve medication adherence. And so such apps and chatbots also raise questions about user agreements and their relationship to informed consent. So in contrast to a traditional informed consent process, a user agreement is a contract that an individual agrees to without a face-to-face dialogue. So most people do not take time to understand user agreements and routinely ignoring them. So moreover, frequent updates of the software make it even more difficult for individuals to follow what terms of service they have agreed to. So what information should be given to individuals using such apps and chatbots? Do consumers sufficiently understand that the future use of health AI apps or chatbots may be conditional to accepting changes to the terms of use? So tackling all these questions are very tricky, and they become even more difficult to answer when information from patient-facing health AI apps or chatbots is fed back into clinical decision-making. So let's now shift to the aspects of safety and effectiveness. So it is helpful, first of all, to know if health AI-based products are regulated. And some products are classified as medical devices under the Federal Food, Drug, and Cosmetic Act, and medical devices are regulated by the FDA. And the term medical device is defined in Section 201H of the Federal Food, Drug, and Cosmetic Act to include an instrument, apparatus, implement, machine, which is intended for use in the diagnosis of disease or other conditions, or in the cure, mitigation, treatment, or prevention of disease that does not achieve its primary intended purposes through chemical action within or on the body of man, and which is not dependent upon being metabolized for the achievement of its primary intended purposes. So on this slide, you can see that there are various regulatory pathways for medical devices. And medical devices, including device software functions, are categorized into 3 classes based on their risk. So class 1 is the lowest risk, class 2 is the moderate risk, and then class 3 is the highest risk. And manufacturers need to choose and prepare the right pre-market submission. And the class of the particular medical device sets a submission type. And so there are 4 common types of pre-market submissions in the US. And that's a 510K pre-market notification or also clearance, the de novo classification request, the pre-market approval, also called the PMA, and the humanitarian device exemption, the HDE. And it's important to know that most AI-based medical devices that are currently on the US market were cleared by the FDA via the 510K pathway. And the 510K pathway usually does not require clinical evidence. Clinical trials are currently rare in the field, but this is likely to be changed in the future. And there are also some software functions that are not considered medical devices and so are not subject to FDA regulation. So in particular, Section 520 of the Federal Food, Drug, and Cosmetic Act contains 5 categories of software functions that are usually not considered to be medical devices, and namely software functions intended for administrative support of a healthcare facility, for maintaining or encouraging a healthy lifestyle. Here, many apps fall under this condition and this category. Then to serve as electronic patient records, and also for transferring, storing, converting formats, or displaying clinical laboratory tests or device data and results. And then lastly, to support certain clinical decisions. So certain clinical decision support software also may not fall under the medical device regulation and are not subject to FDA regulation. And so it's really of utmost importance that health AIs are safe and effective. But how do we actually ensure that health AIs keep their promises? So to ensure the safety and effectiveness of health AIs, stakeholders, particularly AI makers, and regulators need to consider 4 key things. And that's first, the reliability and validity of the data sets and algorithms. Second, some amount of transparency. Third, continuous risk monitoring. And fourth, the system view. So what does that actually mean? So the first key point is that the used data sets and algorithms need to be reliable and valid. And a major concern in this regard is bias. So there are different types of biases, and sometimes they also overlap. And I'm going to show you 4 relevant types of biases that exist with health AI. So first, the slogan garbage in, garbage out applies to health AI, So the better the training data is, the better the AI will perform. And if health AIs are trained on biased data, existing disparities in health may be augmented rather than reduced. And so, for example, the scenario could be that an African-American patient's acrolentigenous melanoma, which is the most common type of melanoma in individuals with darker skin, is missed because a physician trusts a health AI cancer screening device that was primarily trained on white skin. And in some data sets, women are underrepresented, such as data in clinical trials. And so gender bias may occur when such data is used to train algorithms. So it's really essential to diversify data to reflect different populations adequately to ensure fairness. And the lack of patient data of different geographies, races, gender, and socioeconomic statuses may create biases and thus likely prevent the most vulnerable patient groups from benefiting from new health AI-based products. Second, it can also be the case that the used algorithm exhibits bias. So for example, a recent study by Obermeyer et al. Has shown a substantial racial bias against Black patients in a prediction algorithm used by many hospitals and other healthcare systems to identify and help patients with complex health needs. And so bias can really lead to injustice, such as with regard to ethnic origin, skin color, gender, age, or disability. And third, there is a further risk of contextual bias in cases where health AIs are designed in high-income countries like the US for low and middle-income countries. So with contextual bias, even an algorithm trained on representative populations, which is itself a feat, might make improper recommendations. So for example, in a top-ranked specialist clinic, it might be best to recommend to a patient a complex surgery that requires an expert team to manage deadly side effects. However, such a recommendation is likely to kill rather than save the patient in a rural hospital in a low research setting. So contextual bias will be even far more nuanced in most cases. And so we really also need to find solutions to incentivize AI makers to design for low and middle income countries' needs. such as a transfer from one context to another, likely requires retraining the algorithm on local data. It's also essential to involve local people in the design process of health AIs to ensure that these products are useful for low and middle income regions. And then fourth, bias can also be unconscious. So for example, when data scientists choose which parameters to use to help the program learn, they often unconsciously include their own beliefs and values in the code. And so it's really crucial to have a diverse team when developing health AIs to reduce such bias. And so the goal should really be ethics by design rather than after a product has been designed and tested. So stakeholders should try as early as possible in the development process of their product to mitigate biases. So the second point is that in the service of safety and patient confidence, some amount of transparency must be ensured. And transparency really creates trust among stakeholders, particularly clinicians, which is really the key to a successful implementation of AI in clinical practice. And while in an ideal world, all data and algorithms would be open for the public to examine, there may be some legitimate issues relating to protecting investment or intellectual property, and also not increasing cybersecurity risk. Nevertheless, AI makers should be sufficiently transparent, for example, about any shortcomings of the software, such as data biases. And to create transparency, it's also essential that more AI makers publish their work in peer-reviewed literature. In particular, the recommendations of black box systems raise specific concerns. So it will be a challenge to determine how transparency can be achieved in this context. Perhaps there is no need to open the black box. It may be that at least in some cases, positive results from randomized clinical trials or other form of testing will serve as a sufficient demonstration of the safety and effectiveness of such health AIs. So for example, clinicians prescribed aspirin for about 70 years without understanding the mechanism by which the drug works, but they knew that it works. So the third key point is continuous risk monitoring. So regulators currently face what I call the update problem. And to understand what I mean by this, I have to step back a little and give you some background. So some products are legally classified as AI/ML-based SAMD, or artificial intelligence, machine learning-based software as a medical device. And SAMD, so software as a medical device, is defined by the IMDRF, which is the International Medical Device Regulators Forum, which is a voluntary group of medical device regulators from across the world, including the US, whose goal is to accelerate international medical device regulatory harmonization. And the IMDRF defines SAMD as software intended to be used for one or more medical purposes that perform these purposes without being part of a hardware medical device. And the FDA embraced this definition, and under the Federal Food, Drug, and Cosmetic Act, considers medical purposes as those purposes that are intended to treat, diagnose, cure, mitigate, or prevent disease or other conditions. And so SAMD is standalone software that is classified on its own as a medical device, and so is regulated by the FDA. And so for AI/ML-based SAMD, regulators like the FDA currently face the so-called update problem. And so what does that mean? So until now, the FDA has exclusively approved or cleared AI/ML-based SAMD with so-called locked algorithms. And a locked algorithm is defined by the FDA as an algorithm that provides the same result each time the same input is applied to it and does not change with use. And any AI system can satisfy this definition, provided it is fixed in advance. However, such an approach has drawbacks. So suppose an algorithm for analyzing results of mammograms and making recommendations on breast cancer risk receives marketing authorization. And suppose the training data were under-inclusive of African-American women who tend to have differences in breast density from Caucasian women. So the algorithm would make recommendations ill-suited for that population. An SCAI system is used in clinical settings that include more African-American women. it becomes possible to more accurately estimate the parameters used to predict breast cancer in this subpopulation when making recommendations. But the problem is, under current law, any change to the algorithm likely require AI makers to undergo a completely new FDA pre-market review. And so the update may never occur. The maker may not have a financial incentive to pursue the cost of another review, and might also worry about the message it might send about the quality of its existing algorithm. And so most algorithms are adaptive, and that's arguably their key strength. So an adaptive algorithm is an algorithm that may change as it is applied to new data. And it's really this capability to continuously learn that underlies much of the potential benefits of AI. And so regulators like the FDA face currently the problem of whether they should permit marketing of an algorithm that can learn or adapt to new conditions. And if they decide to permit marketing of such an algorithm, they face the follow-up issue of how they can actually ensure that the device is continuously safe and effective. And so for adaptive AI/ML-based SAMD, the FDA proposed in a 2019 discussion paper a total product lifecycle regulatory approach that shall permit continuous improvement of such devices while maintaining their safety and effectiveness. And so without going into the detail here, so one major idea from the FDA is that the AI/ML-based SAMD could be updated to a certain extent after marketing authorization. So when seeking initial pre-market review of an AI/ML-based SAMD, manufacturers would be given the option to submit a so-called predetermined change control plan, which would contain a description of anticipated modifications and an algorithm change protocol, including the associated methodology being used to implement such changes. And so the FDA, without doubt, is currently ahead of other regulators in thinking about these issues. However, the FDA's recent attempt to wrestle the update problem can be improved by focusing particularly on continuous monitoring and risk assessment, and less on articulating ex-ante plans for future algorithm changes, because AI makers will often not know in advance the sorts of changes that might be needed. And so such monitoring should really focus on new risks due to AI/ML characteristics, such as instability. So for example, similar patients should be treated similarly. That is, medically insignificant differences among patients should not lead to substantive differences in diagnosis of treatment. So from the perspective of patient safety, it's really undesirable to have an algorithm that is not stable. And for example, frequently classifies medically similar skin lesions very differently. In general, regulators like the FDA need to widen their scope from evaluating medical AI/ML-based products to assessing systems. So this shift in perspective from a product view to a system view is really central to maximizing the safety and efficacy of AI/ML in healthcare, but it also poses significant challenges for agencies like the FDA, who are used to regulating products and not systems. So an AI/ML-based SAMD is usually one part of a larger system involving various kinds of human involvement. So from healthcare teams inputting the data, to physicians reacting to AI recommendations, to insurers deciding whether to reimburse only for certain course of action. It's really this entire system that must be evaluated, a concept that my co-authors and I call the system approach. And so in a sense, it may be useful to reframe what hospitals and practices are doing. So they are not merely buying an AI/ML-based tool, but hiring one. Cognitive testing of a physician will not tell you how they will do when added to a pre-existing team in a particular health system. And employees need to be continuously assessed. And the same is true for AI/ML-based SAMD. In January this year, the FDA also published its new action plan on AI/ML-based SAMD, and in particular, the FDA has 5 goals. So first, further developing the proposed regulatory framework, including issuing draft guidance on a predetermined change control plan. Second, supporting the development of good machine learning practices to evaluate and improve machine learning algorithms. Third, fostering a patient-centered approach, including device transparencies to users. Fourth, developing methods to evaluate and improve machine learning algorithms. And then lastly, advancing real-world performance monitoring pilots. And in this new action plan, the FDA has also recognized our paper on the system view, which is really encouraging to see. Let us now have a look at some of the questions of liability. So even when an algorithm are trained as well as possible, they may, for example, miss a tumor in a radiological image or suggest the incorrect dose for a drug or an inappropriate drug. And sometimes patients will be injured as a result. And so one crucial question that arises is, when could a physician likely be held liable under current law when using health AI? And in general, to avoid medical malpractice liability, physicians must provide care at the level of a competent physician with the same specialty, taking into account available resources. So the situation becomes more complicated when an AI recommendation becomes involved. And in part, that's because AI is so new in clinical practice, there's essentially no case law on liability involving health AI. Nevertheless, it's possible to understand how current law may likely to treat these situations from a more general tort law principle. So my wonderful colleagues, Professor Nicholson-Price and Professor Glenn Cohen and I, we published a viewpoint in JAMA in 2019, in which we discussed when a physician could likely be held liable under current law when using medical AI. And this chart presents potential legal outcomes for simple interaction. So for example, imagine an AI that recommends the drug and dosage for a patient with ovarian cancer, and assume the standard of care for this patient would be to administer 15 milligrams per kilogram every 3 weeks of a particular chemotherapeutic agent. And there are two scenarios, namely scenarios 2 and 7, in which the physician could likely be held liable when using AI. So let's have a look at scenario 2. So if the AI recommends the standard of care dosage, which is 15 milligrams per kilogram every 3 weeks of the chemotherapeutic agent, and the AI is correct, but the physician rejects such recommendation, the physician will likely be held liable for injury to this patient. Let's have a look at scenario 7. So let's imagine that the AI recommends now the non-standard of care dosage. So for example, a much higher dosage, such as 75 milligrams per kilogram every 3 weeks. But this time, the AI is incorrect and the physician follows the AI, then the physician will likely be held liable for harm to that patient. And so under current law, the physician faces liability only when he or she does not follow the standard of care and an injury results. So our analysis suggests an important implication for physicians using medical AI to add their clinical decisions. So because current law shields physicians from liability so long as they follow the standard of care, the safest way to use medical AI from a liability perspective is as a confirmatory tool to support existing decision-making processes rather than as a source of ways to improve care. But the standard of care is, of course, not forever fixed. It may well be that someday AI becomes part of the standard of care. And if and when that happens, the physician will likely be held liable only in the case where he or she does not follow the AI recommendation and an injury results. So we have also a follow-up piece based on a study by Tobia et al., which was recently published in the Journal of Nuclear Medicine. And interestingly, Tobias et al.'s empiric study found that potential jurors indicated that not only following the standard of care could result in no liability for physicians, but also independently, so could following the advice of the AI system. So if a physician followed an AI recommendation to deviate from the normal standard of care, and the AI was actually incorrect with patient injury resulting, potential jurors were fairly likely to find that decision reasonable. Let us now have a look at some of the data privacy issues raised by AI in healthcare. So the Health Insurance Portability and Accountability Act, HIPAA, the privacy rule, is really the key federal law to protect health data privacy in the US. And however, the problem is that HIPAA has right now significant gaps when it comes to today's healthcare environment, since it only covers protected health information generated by covered entities or their business associates. And so protected health information isn't generally individually identifiable health information. And HIPAA-covered entities include health plans, such as health insurance issuers, healthcare clearinghouses, such as billing services or repricing companies, and also healthcare providers who transmit health information electronically in connection with particular transactions. And a business associate is a person or an entity that performs certain functions or activities, such as data analysis or processing, on behalf of or provide services to a covered entity that involves the use or disclosure of protected health information. And so HIPAA does not cover health information generated by entities not covered by HIPAA. And in particular, much of the health information collected by technology giants such as Amazon, Google, Microsoft, Facebook, and Apple that are usually not covered entities will fall outside of HIPAA. However, in some cases, HIPAA-covered entities such as healthcare providers use the activities or services of companies such as Google and share protected health information with them. And in such cases, the top companies are business associates under HIPAA, and a business associate agreement between the parties will then typically contain appropriate safeguards on the use or disclosure of the shared individually identifiable health information. So a different problem with HIPAA is its reliance on de-identification as a privacy strategy. So when, for example, hospitals share data with Google and Co., they often make sure that the data is de-identified. And de-identified health information can be shared freely for research and commercial purposes. And de-identification is usually done by the removal of 18 identifiers, such as names, social security numbers, and biometric identifiers of the individual or of relatives, household members, or employers of the individual. And the covered entity does not have actual knowledge that the information could be used to identify the individual. But HIPAA may not adequately protect the privacy of patients because of the problem of data triangulation. So a person may be de-identified as to one data set, but the data may be easily re-identified through the combination of another available data set. So for example, since Google has easy access to other information, such as through Google Maps, re-identification is not very difficult in most cases. And so it's not surprising that this problem has already been picked up by a recent lawsuit, Dynasty versus Google, in which the plaintiffs alleged that the University of Chicago Medical Center shared medical records with Google containing enough information that enabled Google to potentially re-identify patients given all of its other data at hand. However, this lawsuit has recently been dismissed by a federal judge in Illinois on the grounds that Matt Dynasty did not demonstrate damages. And this case really demonstrates the challenges of pursuing claims against hospitals that share patient data with tech giants such as Google. So for all the reasons explained, HIPAA is not adequate to protect the health privacy of patients in the big data world. So other jurisdictions have implemented other regulatory designs, such as the EU. So the General Data Protection Regulation, the GDPR, has been applied since 25th May 2018 in all EU member states and introduced really a new era of data protection law in the EU. And it protects fundamental rights and freedoms of natural persons, and in particular, their right to the protection of personal data. So the GDPR is a lot broader in its material scope compared to US HIPAA and applies to all personal data, including data concerning health. And it's also has a wide territorial scope, and in some cases even applies to US entities, such as in cases where the processing activities are related to offering of goods or services to data subjects in the EU. So while HIPAA preempts protective state law, it does not preempt states whose laws are more protective. And California recently has taken action at the state level. And the California Consumer Privacy Act of 2018, the CCPA, became effective on January 1st, 2020. And the CCPA grants various rights to California residents with regard to personal information that is held by businesses. And the CCPA does not apply to protected health information that is collected by HIPAA-covered entities or their business associates, but it applies to a great deal of information in so-called shadow health records. So that's health data, which is collected outside of the health system. And so the CCPA is really a welcome attempt to at least partially fill in legal gaps and improve the data protection of individuals. And only this March, Virginia became the second state to pass comprehensive privacy legislation. And the Virginia Consumer Data Protection Act, the CDPA, will come into effect in January 2023. However, the CCPA and CDPA only applies to California and Virginia residents. And so individuals currently depend in the US on the privacy laws of each state to what extent their privacy is protected. So let's come to the conclusion. So as we have seen, the use of AI in healthcare has really enormous potential to transform it for the better. However, health AI also raises many ethical and legal issues. And in particular, there is a need to examine under what circumstances, if at all, the principles of informed consent should be deployed in the clinical AI space. And there are 4 key things to keep in mind to ensure the safety and effectiveness of health AIs. So first, the reliability and validity of the data sets and algorithms, some amount of transparency, continuous risk monitoring, and the system view. And so in this context, a major concern what we have seen is bias. Yeah, so there are different types of biases, such as training data, algorithmic, contextual, and also unconscious bias. And the ethical issues, such as biases, should be considered really at the earliest stages of the development process of such products. The goal should really be ethics by design rather than after a product has been designed and tested. And transparency really creates trust among stakeholders, particularly clinicians and patients, which is a key to a successful implementation of AI in clinical practice. And regulators should prioritize a continuous risk monitoring approach and really focus on risk due to features that are specific to AI systems, such as instability. And regulators like the FDA need to widen their scope from evaluating products to assessing systems. And as AI enters medical practice, physicians need to know how law will assign liability for injuries that arise from interaction with AI. And it's really of pivotal importance that we adequately protect the privacy of individuals, especially patients. And as we have seen, HIPAA has significant gaps when it comes to today's healthcare environment, and much of the health information collected by tech companies, such as Google, will fall outside of HIPAA. But the GDPR, the CCPA, and the CDPA are really welcome attempts to improve the data protection of individuals. And with that, I thank you so much for your attention, and I look forward for any questions in the Q&A.
Thank you, Dr. Jerky, for that amazing presentation. We'll now be taking questions from the audience. So one of our participants is asking if AI has all these capabilities, as you mentioned, would it have the ability to make operations like injecting a person with a vaccine or even performing a knee surgery?
Yeah, so this is a very good question. And actually AI, so what a big field will be in the future is AI in surgery. So we already see there AI assisted surgery, which will probably become available and in the near future, and probably in 10 years from now or so, even that it will be autonomous surgery. So right now, what will be developed is AI-assisted surgery, but of course, we need to figure out all the questions, ethical and legal questions around it. But that's something where AI will be in the future being used, yes.
Thank you. And one of our other questions is another one of our participants is asking, in which situation would locked and adaptive algorithm best be suited for in medical care?
Yeah, so this is also a very good question. So as I mentioned, adaptive algorithms are probably more beneficial because they can adapt to new situations. But at the same time, of course, they also raise challenges because of the fact that they continuously learn. So you need to constantly monitoring them to make sure that they don't introduce through the learning process other biases, which makes it inaccurate for some subpopulation, which is very important to always check them. But of course, the locked algorithms, they also always need to be updated. And if the update does not happen, then they could be actually also problematic for some patient subpopulations.
Thank you, Dr. Jerky. So our team, the GCL California team, also has some questions for you. So first up, what introduced you to the fields of ethic and legal issues with AI? And are there any specific people or projects who have inspired you?
Yes, thank you so much for that question. So I believe, so I'm a healthcare scholar, so I always worked, I was very interested all the time in ethical and legal questions, which were in relation to medicine. But I really saw when I got into the AI space, I really a couple of years ago, I really saw that AI can actually help and improve healthcare and has a lot of potential. But it also raises unique and really new challenges, which are so complex that we need to bring in all kind of stakeholders to actually being able to solve them. And I think it's a very important work, because if we do it right in the society, we can actually help many people around the world to get better access to healthcare and better healthcare. But for that, we need to work all together and really making that happen.
Yeah, definitely. Another question we had for you was relating to your mention of how HIPAA doesn't cover certain entities. So do you think privacy regulations should be expanded to other areas of the world, like on a national level instead of just on the state level in the US?
Yeah, that's also a very good question, and I highly believe in that. I believe we need in the US something similar to the GDPR, where it really is a federal law which supersedes the state law, so that every individual, no matter where you are living, is properly protected, the privacy. Yeah.
Okay, and finally, we have, what ethical questions do you think that students learning about and building their own artificial intelligences need to consider?
I think one very big one is bias. I think from the beginning, when you are developing the products, you need to be in a diverse team and need to be really thinking critical about your product, what data you are using, make sure thinking about the data, what kind of potential biases could exist, how can you mitigate them? And I think you need to test them in different local sites, and doing as much even clinical testing as possible, and not just in the lab scenario. So, but then also trying to go to different testing it and validating it in different hospitals too.
Okay, thank you so much, Professor Jerky, for your time and your wonderful speech. We will now.
You're welcome, my pleasure.
Yes, thank you. We will now be moving on to our lunch break and then our next workshop. Thank you so much, Dr. Jerky.
Thank you for having me.
Thank you.
Bye.
Thank you.
Okay, so we'll be moving on to the lunch break, and I'll be setting a timer for you guys to reference for how much you have left. It'll be lasting an hour, and let me share my screen real quick. And I also want to say thank you so much to Professor Jerky. Like, that was a great workshop, and I've really appreciated all the questions from the audience also. So let me go ahead and start this timer, and we'll be starting again in approximately 1 hour. So that would be 12:45 a.m. PDT or PM PDT. And then let me start this right now. And I will just start some lo-fi and we will convene in an hour. Thank you. Okay, so we're going to be wrapping up our lunch break. I hope you guys were able to grab something to eat. And Swathi, if you could introduce Dr. Shelton for his presentation.
Yeah. Hi, Dr. Shelton and everyone. It is my great pleasure to introduce our next speaker, Dr. Christian Shelton. So Dr. Shelton is a professor of computer science at the University of California at Riverside and a member of UCR's Data Science Center. He has been on the faculty since 2003. His research interests are in statistical approaches in artificial intelligence with a focus on machine learning and dynamic systems. He has applied his work to areas ranging from astronomy, sociology, and medical informatics. He has over 70 critically peer-reviewed publications and has been awarded over $1.5 million in SolPy grants and over $2.5 million as his portion of CoPy grants. He has graduated 13 PhD students and 12 MS students. Dr. Shelton is a member of Tau Beta Pi, the National Engineering Honor Society, and Phi Beta Kappa, the National Liberal Arts and Sciences Honor Society. He received the Young Investigator Award from the Air Force Office of Scientific Research and was a member of DARPA's Computer Science Study Group. Now, on to Dr. Shelton.
Thank you very much. Hopefully I'm audible, and if I can do this properly, I will share. Let's see if this works. That seems not to work. This was working a moment ago. Well, I can switch to another method here if this is not. You seem to not be able to see my second camera. Let me just cancel this method and try a different method here altogether. We'll just try an old school. I had until recently a nice green screen and everything else set up. But then I tore it down in my house and came into work because now we get to work. And so I can't do that. But let me just, so we're going to do this the old school way. I'll have a box in a box. There. Is my screen visible?
Yep, everything's all good.
Great. And you can hear me?
Yep.
That's
perfect.
always a positive. Terrific. Thank you. I'm excited to be here to talk to you today about some stuff that I've done in my research group at the intersection of machine learning and healthcare. So I'll jump right in. I'll attempt to monitor the chat if people have questions or things, or if you just want to shout something out, and I'll certainly try to save some time at the end for any questions that you might have. Since I'm talking about machine learning, I'm talking about healthcare. I'm going to talk a little bit first about what is machine learning and what is healthcare. And of course, this is my opinion or my point of view. It's not horribly far off from most, but ask 10 people and you'll get 10 slightly different opinions here. So I'll try to orient this. If I had to describe machine learning in a single sentence or something, it's trying to answer the question, how can computers improve with experience? There are, of course, a set of problems and a set of techniques that this encompasses. So I've drawn them here as this, purple circle. Within machine learning, there are probably some terms you've heard about. Neural networks. Neural networks are essentially an approach to function approximation. So that is, if I have some data points, you could fit a line to them, right? To try to do regression, to try to figure out what the relationship is between the X and Y variables. But a neural network is sort of a more complex sort of method of doing that. It's a component of machine learning. So people who work in neural networks would consider themselves working in machine learning, but not everyone in machine learning works on neural networks. And within machine learning, there's this popular thing called deep learning, which is a particular sort of subclass even of neural networks. My talk's actually not going to involve any neural networks or deep learning, although you can relate anything to anything else. I'm sure we could relate it there, but my talk's actually not going to involve any of that. Machine learning grew out of, or as a term that really came from artificial intelligence. Artificial intelligence started as a field, the name started sometime in the 1950s. People have been thinking about it, of course, for centuries, really. If I had to define artificial intelligence in a single word, phrase, which is kind of hard to do, I'd say it's getting computers to do things you thought only humans could do. Which means that essentially once we succeed in a task in artificial intelligence, it gets thrown out of artificial intelligence. So it's almost a self-defeating field of study. But machine learning is the name given to people working, the name given by people working in artificial intelligence to this idea of, oh, well, one thing that you think humans do is improve with experience. There's an older field, the field of statistics, which has for a long time been talking about how do you analyze data, and experience is just data of a particular form. And so statistics has a lot to say about how you analyze data. And indeed, a lot of people in machine learning probably consider themselves statisticians before they consider themselves AI specialists. So there's some overlap there. And then there's a new field of data science, which is maybe the past 10 or 20 years or so. This term has come to encompass a whole variety of activities surrounding data, including how to store and manipulate, and then also how to interpret or predict with it. And that's where the machine learning or statistics comes in on the side there. So there are certainly, what I'm going to talk about is sort of at the intersection of AI, statistics, and data science in some sense. As I said, I'm not going to talk much about neural networks or deep learning here, but that just sort of orients you. All of these are human-invented terms to describe human activities of research in a way that we see how subjects come together. None of them is an inherent property of the universe or anything like that. And so in that sense, they're kind of fuzzy. You know, different people have different views of them. And there's not a hard line of what is or is not machine learning or data science or statistics, but this gives you maybe a little bit of an overview if you haven't seen a figure like this before. Okay, so how about healthcare? Healthcare is huge. You know, it's probably the largest industry, at least in the United States, in terms of amount of money spent on it. So instead of just telling you what healthcare is, maybe I'll talk about what problems might be tackled using machine learning. How can machine learning help in healthcare? And so I sat down and I wrote a dozen of them, and I just stopped at a dozen because, you know, I could keep going on and on, but I stopped at a dozen, figuring to give you some idea. The ones on the left are maybe a little more immediate and obvious and related to maybe more health, and the others are more related to the care setting, maybe. So disease diagnosis, you know, can I look at the signs and symptoms, use past data to build models that would let me predict, maybe do prediction of disease or what the disease diagnosis might be? Can I build systems that look at chest x-rays, that look at brain MRIs, that look at CT scans, and maybe interpret those images, maybe point out interesting things, maybe build diagnoses from the images? Drug manufacturing itself relies fairly heavily on machine learning to give ideas of what compounds might be tried. You can talk about effect prediction. That is, if I were to try this intervention with this patient, what might happen? That's quite tricky. Medication interaction. There are billions of, well, not billions, there are thousands of medications out there. This one and that one perhaps have never been tried by the same person together, or maybe not that much, but maybe we can mine some information from past patients to figure it out. Over here, we have some things that maybe aren't as clear, but are just as important. Interpreting clinicians' notes. Clinicians write down notes in sort of a shorthand with lots of abbreviations and such. Oftentimes you'd like to sort of bring that out of the mind of the doctor or the nurse or somebody else and more interpretable. Benchmarking, just because, you know, your hospital has a 5% mortality rate and my hospital has a 10% mortality rate doesn't necessarily mean that your hospital is better than my hospital, because they see different cohorts of patients. Maybe my hospital just sees sicker patients. And so establishing benchmarking is often used, some machine learning there. Triage in mass casualty situations, who should get treatment, who shouldn't. You can look at past data to try to estimate what would be the value of giving out treatment when that treatment is limited. Clinician scheduling, can you predict who maybe you should have on call or in the OR or the ER or the ICU at any particular time? And then, you know, visualizations to doctors, managing drug trials so they can be more efficient, maybe and adaptive. All these things are different problems in healthcare that people are looking at addressing with various parts of machine learning. I'm not going to talk about all of them. I was told I did not have 3 days to talk to you for. So what I'm going to talk about is largely in the area of disease diagnosis and maybe a bit of disease prediction, which are being sort of the most straightforward. And I'm going to talk about one thing that worked. But before that, I'm going to talk about one thing that didn't work, but I think it didn't work in an interesting and informative way. So I'm first going to tell you about one of my failures, and then I'll tell you about one of my students' successes. But first I should thank, this work started when I was on sabbatical. I got a 16-month break from my current job to go work at Children's Hospital Los Angeles, which is in Los Angeles. It's run by University of Southern California. And I worked with their pediatric intensive care unit and the clinicians, the doctors and nurses and other people there who run the pediatric intensive care unit. This is for sometimes the sickest of children, ages 0 to 18, not the neonatal intensive care unit, not the cardiac intensive care unit, but anybody else would end up here. These are the doctors I worked with. The top Randall runs the unit. Robbie was the one I worked with most primarily, but I worked with also Nelson, Christopher, and Patrick. Behind them are a whole team of engineers. Computer scientists and computer engineers and data scientists who help make sure that all the data is available, work on the databases, do other sorts of projects there. And I've listed them down here at the bottom. I worked with all of that team too to get the data. It maybe doesn't draw as much attention as it should. It's a very key part of this. Some of these people aren't still there. Some of them have moved on to other jobs. This was started almost a decade ago, but these are the people I worked with for these studies. Okay, I'm not seeing any questions yet. I think that's because there are no questions, but if that's not the case, someone should yell at me. I mean, nicely yell at me. Okay. So this is a bed in a pediatric intensive care unit. It's not the one at Children's Hospital. I didn't have permissions to show that one, but this one here. What dominates this picture are computers, machines that record things, that make semi-automated decisions, you know, monitor and that sort of stuff. The arrows there to show you there actually is a patient here. There's a very small baby inclined on that table there, head towards us. But most of this is a large data gathering apparatus. And so with all that data gathered, we'd like to be able to do something with it. Take all that, what's now retrospective data. So we aren't running experiments on the patients, please understand that. We're just recording what did happen under normal care, but maybe we can, you know, deduce some useful things from that. So, so that data is medical health data. Medical health data has been collected for over 100 years, and well, for thousands of years in some form. Over 100 years ago, there was the first sort of centralized paper medical charts. And in the 1970s, when computers were the size of rooms or at least closets, some hospitals and healthcare providers started putting electronic medical record systems together. That was really driven in maybe the past 20 years by federal laws and such. And now pretty much everybody has some sort of electronic health record. Every hospital has some sort of system that way. A medical health record will contain a whole bunch of different stuff. I'm not going to go over everything that's in here, but all of this stuff at some point is your medical health data. In a commercial EHR, almost all of this gets captured. High frequency measurements like an EKG waveform or things like that often don't make it into the EHR, the electronic health record. But the rest of this often ends up there someplace. The diagnoses are sometimes hard to pull out because often they're just buried in the free text that some doctor scribbled off with a bunch of abbreviations. These systems were designed to make sure people got billed properly. So really, the best data here is on the billing codes, but you can't use that because it was designed for billing purposes. I mean, you can use it, but it's not going to tell what you want. But it's there, so we'd like to be able to use it. These top things are essentially like direct measurements of the patient. There's very little interpretation there, sometimes referred to as the physiome, not a word I particularly like, but that's what we're going to be looking at here. And we're going to be looking at it for the pediatric intensive care unit. So your electronic health record records stuff no matter where you are in the hospital or outpatient clinic or something else. We're going to look at a pediatric intensive care unit because it's a relatively short period of time with a defined outcome and relatively carefully monitored. So they're much more frequent observations than you'd get if you were just in the general ward or of course at home and only seen, once every few months. At CHLA in particular, just to give you some sense, there are, at least 12 different databases containing different kinds of information. I'm going to look basically at these top two, which are basically from two different systems, two different vendors. They changed vendors. That whole engineering team was necessary to sort of merge these databases together, figure out which things were necessary from which and how they match together so we get a coherent view. Present in this case is like 2014. So at that point, we stopped it and just analyzed data from there. We have about 15,000 patient episodes, although not all of them are applicable to every study. Okay. So what does that data look like? Well, this is real data from 3 patients during their first 24 hours in the intensive care unit, which is sometimes the most critical time in the intensive care unit. Lots of things get measured. Most common are things like vital signs. So heart rate, respiratory rate, blood pressure, systolic and diastolic here. This is time going across the horizontal axis, and the vertical axis is the value. You can see they're not recorded regularly. They're mandated sort of recorded every hour, but at this point, maybe the patient was off in the operating room or something else, maybe over here. Here something was happening, and so they were recording it more frequently. This measurement here entitled CO2 is only gathered when the patient's been intubated, something I'll discuss in a bit. It's the amount of carbon dioxide they're exhaling. So you can see that the fact is being recorded itself even tells you something. That means this patient's on a ventilator. Here are different interventions. Each row means just some different intervention, like they perform CPR. It's probably not on here, other sorts of things. If it's a continuous intervention, it's by a line. So this is probably they were on a ventilator. These 2 patients were, this patient was not. I don't remember what all these symbols are, but different things that they can sort of do to you in the ICU. So a bunch of these happen at the same time. There must be sort of a single thing. And then medication. So this doesn't tell you the amount, it just shows you which drugs are being administered. A solid line indicates it's some infusion, a drip through an IV. The single symbols are boluses, just something taken orally or an injection just all at once. So we have this for thousands of patients. The idea is probably there are patterns in here. There are things that we'd like to learn. Can we do that automatically with the computer? All right. So the first thing I want to talk about is the thing that did not work, but I think it did not work in an instructive way. And that involves predicting creatinine levels. So creatinine is a molecule. Here's its chemical formula. It has 2 sort of conformations that it exists in. It's produced by your muscles at a relatively constant rate. And it goes into your blood, and then it's filtered by your kidneys, and it goes into your urine, and you pee it out, and you get rid of it. Okay. If your kidneys are injured, then often they won't be filtering creatinine levels as they should be, and the level of creatinine in your blood will rise, which is generally a sign of acute kidney injury, which can happen to, 5 to 10% of the patients in a pediatric intensive care unit. Sometimes actually kidney injury was the better of the 2 options the clinician had, but sometimes maybe we could have stopped it and we known that it was going to happen sooner. So the goal here is to predict the creatinine level of a patient in the future, and if it looks like the creatinine level might go up, to warn somebody about it. So imagine we have a single patient. This is a bit of a cartoon, but a useful cartoon, I think. We have various different measurements. Some of them are continuous relatively over time. Like let's say their creatinine level, we're measuring that regularly. Some of them are not. Maybe they're on a drug here, they're on some other drug over here. Then at some time, we think about it and say, okay, given all this information I've accumulated in the past about this patient who's been in my ICU for, I don't know, 36 hours, can I predict what their creatinine, their blood creatinine level will be, let's say 2 days from now? Hey, and then I can say, oh, if it's going to go up, maybe I should warn somebody about it. That makes sense as a sort of method? Okay, good. So that's the idea. So what we're going to do is pull data from these thousands of patients. For all of them, we'll just sort of pretend at some moment in the middle, that's now. I only knew this stuff to you before here. Because this patient actually has already been discharged, I know what their creatinine level will be 48 hours now. And so I can build sort of, I want to predict this value from these values here and I have a bunch of examples. This patient who looks like this at this moment, 48 hours from then, had a creatinine level of this. This patient, 48 hours from then, has a creatinine level of this. And I get a bunch of pairs, a bunch of examples of this history led to this creatinine level and this history led to this creatinine level. Can you find a function that in general maps the history to the future creatinine level? That's the goal. We're going to use machine learning to do it. It's just basically a simple regression problem. If you imagine there was only one variable I was observing over here, it's just, I plot them out and I try to draw a line or something else that explains one from the other. In some sense, that's what machine learning does. It does it a little more complicatedly, but that's what it does. And the computer does it automatically. So I don't plot it and I don't draw the line, which makes me feel good. That's why I have a computer in the first place, because I find that tedious. So there's a challenge from the the medical's perspective, which is that everybody has a different base level of creatinine that should be okay in their blood. And everybody has a different amount that sort of means it's gone up too high. So you have to sort of normalize these, and these can vary drastically from children. The proper creatinine level for a 6-month-old and the proper creatinine level for a 16-year-old are fairly different. And it depends a lot on how much muscle mass you have, a bunch of other things. We did some data normalization. This involved talking to clinicians and understanding like what might be sort of constant across patients, what might be a good thing to predict that actually would be, sort of consistent across patients. I'm not going to go into all that, but I do want to point out that's an important part of anything here is to understand what problem you're really working on, not just to apply the machine learning blindly. The second challenge, though, is that I measured, 100 different things over here. By chance, just by accident, some of them will appear to be correlated with the future blood creatinine level. However, that isn't actually predictive. It's just, by happenstance. Okay. So I don't want to just take anything that's correlated. I want to take something that's really has a very strong statistical correlation or predictive value there, so that I'm sure that it's not just by accident. This really is predictive. And there are machine learning methods to do that, to automatically sort of select a subset of the variables, subset of these measurements over here to say those are the ones that really should be used to predict the future blood creatinine levels. So we're going to do that. And we're going to try a whole bunch of different methods, and they all sort of come out to the same answer, which foreshadowing is a bad answer, but here we go. Okay. So what happens? You say, please, I bet there's a lot of noise in this data. Only tell me something that really, really is predictive. If it's only kind of predictive, I'm not going to believe it. I think there's a lot of noise in this data. And the machine goes off and it crunches for minutes or hours or whatever, and it comes back and it says, aha. Well, okay, it doesn't say aha, but if you read what's on the screen and you think about it, it's aha. What's really predictive of your blood creatinine level 48 hours from now? Your blood creatinine level right now. Well, sure. Yeah. Right, good. Sometimes good. If it didn't say that, we'd be worried. But that's not very helpful to just tell the doctor, what I think the creatinine level will be 40 hours from now is what it is right now. That's not very helpful. I could have done that myself. Okay. So you say, well, maybe there isn't quite that much noise in the data. Maybe there's something else that's predictive there. Please try again. So you rerun your method and you get another result, which is that not just the current blood creatinine level, but also whether or not the patient is on a nephrotoxic drug is predictive. You think, aha, this is amazing, fantastic. I didn't even tell them they were nephrotoxic drug. I just said, here's a category of drugs. Nephrotoxic means damaging to the kidneys. Fantastic. That's exactly what I would expect. I mean, again, maybe not too surprising, but at least we're on to something here. You say, that's great. And then you look more carefully, as I did about 5 minutes after I made this discovery, and it has the wrong sign. So that is, the model or the predictance says, if you're on a nephrotoxic drug, then you are less likely to have your blood creatinine level to go up. You are less likely to get acute kidney injury. Whoa. And so, you know, you check your results, you think, oh my gosh, did I screw something up? No. That's definitely the answer. And it's definitely true. It's definitely true that if you're on a nephrotoxic drug, that is, being on a nephrotoxic drug is correlated with having a less chance of your blood creatinine level rise if you're in an intensive care unit, pediatric intensive care unit. Any ideas why? It took me a few minutes. I have some experience with this, and I understood why. I don't know if it's fully obvious. Why would that be? Well, let's put it this way. Are you familiar with the term that correlation is not causality? This is critical. Correlation is not causality. Okay, so it is true that being on a nephrotoxic drug is correlated with a slower chance of having acute kidney injury, but it's not because a nephrotoxic drug reduces the chance of acute kidney injury. No, in fact, if anything, I guess it increases it. It's because those two things are both correlated with something else. Okay, they're both correlated with the patient having a fairly robust and healthy kidney. That is, the patient was only given a nephrotoxic drug because the doctor already determined through other things, maybe stuff I didn't even measure, that the patient was not at risk for getting acute kidney injury. If the patient had been at risk for getting acute kidney injury, doctors aren't stupid. They go to a long, deal of medical training and such, and they've seen a bunch of stuff, right? If they already thought it is a child. If the child was at risk for acute kidney injury, they wouldn't have given them the nephrotoxic drug in the first place. So the fact the patient is getting the nephrotoxic drug is a sign that due to other factors that I can't observe here, this patient has a relatively healthy kidney, which means that it's less likely, just all other things being equal, that the blood creatinine level will rise. Great. So correlation is not causality. Oh gosh, if you take only one thing out of statistics or anything else, take out correlation is not causality, okay? The two are completely separate. In order to get causal effects, I have to run experiments where I intervene and change the natural course of events, which we do not do in the pediatric intensive care unit, okay? At least not without a lot of medical approval. We did not do any of that here. So you have to be able to do that. That's not what's going on here. This patient is under observation and careful attention, the most careful attention medicine has to offer from skilled doctors. So if I'm going to discover anything in this little process, I have to discover something that clinicians already wouldn't have been adjusting for, because the data I have already has those adjustments taken out, right? If the blood creatinine level looks like it's rising, they'll already adjust it over these 48 hours. So I have to figure out if it's going to go up beyond which the sort of the hospital system already knows. Yep. So that's critical. So that's why this failed. Okay. Let me talk about, oh dear, I took too long, but that was important. Let me talk about something that succeeded. I'll try to do it as quickly as I can. I think I can fit it here. So this is the PhD work of a student of mine, Bushra. She's now a machine learning scientist at Amazon Comprehend Medical, a division of Amazon that works on similar problems. So she moved up to Seattle and has continued to publish papers in this area. I've taken these slides more or less from her dissertation defense, actually. But she did such a nice job putting them together. I appreciate it. Okay. So in an ICU, especially in a pediatric intensive care unit, one of the primary reasons that children end up in there is because they're going to need ventilation. That is, they need to have generally a tube put down into down their throat a pretty long way, attached to a machine that then either completely or partially helps them breathe. At Children's Hospital Los Angeles, which is a tertiary ICU, so it sees the sickest of children, about 40% of the patients at some point, if they're in the PICU, will be ventilated. This is a picture of some small child under mechanical ventilation. When you're under mechanical ventilation, the big picture is they measure a bunch of things about you, like how much oxygen you exhale, hopefully not very much, how much carbon dioxide you exhale, hopefully a lot, how much oxygen we put in, how fast you're breathing, how much volume goes in and out, all these sorts of things. There are also a bunch of knobs that they can turn. Okay, so they turn these knobs, like how hard the thing pushes, or how much volume it tries to put in, or how much oxygen is in the air that they put in. Okay, it tries to adjust these knobs to help the patient as quickly as possible recover and then get off the ventilation. So we're talking about the acute phase of ventilation where the patient is the sickest, not the weaning phase where the patient is more or less stable and they're just trying to get them off the ventilator. In order to do that, we need to know the oxygen level of the blood, the carbon dioxide level of the blood, and the pH of the blood, because these three things are what your lungs are trying to control. We can put that little clip on the end of your finger to figure out, I don't do it. I'm not that kind of doctor, but other people can do that. Put the little clip on the end of your finger to figure out how much oxygen you have in your blood. But for carbon dioxide and then indirectly the pH, the only solid way at the moment is to take a blood draw. So here's a very small person's arm. They're taking blood. The more frequent I can take those blood draws or get an estimate of these blood gas values, how much carbon dioxide and pH of the blood, the more frequently I can adjust those knobs and the better I can manage the ventilation. The problem is the blood draws are kind of a pain. They can't be done that often. And in children, especially small children, they can be difficult. So I'd like to have a non-invasive estimate, just like that clip on your finger. The idea is that there are some things I can never observe, like how the lungs are working, how much space in the lungs is actually healthy at this moment, things like that. There are a bunch of things around that, though, that I do observe that are related. The heart rate, the blood pressure, how much volume is being pumped in and out, how much oxygen I'm pushing in, how much carbon dioxide is being exhaled. That's a very important one. Some of those, like the partial pressure of carbon dioxide in the blood or the pH of the blood, those are invasive measurements. I have to draw blood, take it over to the machine, read it. But most of the rest of these are non-invasive measurements. And so the question is, can I build a model of this system? This is a dynamic system that changes over time. Can I build a model so that by observing these things in blue, I can estimate statistically what's going on with these things in orange? The lung injury score is not relevant for this particular thing. The answer is yes. We're going to take a training set. So the answer is yes. I'm going to build a statistical model of how these things relate over time. And I'm going to use that so that any given instant, I can look at what things I have measured in the past. So both the blue variables and if I've taken blood gas values before, the orange variables in the past, and relate them to what I predict if you were to walk over the machine right now with a drop of this patient's blood, what carbon dioxide and pH I would get. And of course, I have examples of when I actually did go over to the machine. So I can see, well, if I were to guess, how accurate would I be with this model? If I were to guess, how accurate would I be with this model? And we're going to use about 275 children from Children's Hospital Los Angeles to build the model, but then we're going to test to see how well the model works by looking historically, like if I had used it instead of using the blood gas machine, on 6 children from 6 other centers who, of course, were under different sort of slightly different conditions under different standards of care to see how well it generalizes. This is just an example of the 3 patients. You can see it's not measured regularly. It jumps all around. It's kind of a hard problem. This slide's supposed to tell you it's a hard problem. We actually did some work. That's what it's supposed to tell you. Okay, great. There are some current models, some current simple models that use sort of ratios of things or this Henderson-Hasselbalch equation to attempt to predict what it would be. So we're going to compare against those because that's what the standard of care at the moment is. So I'll show you that in a moment. Okay, we're going to use what's called a multivariate Gaussian process. Sounds very sophisticated. It's not that sophisticated. But what it does is it basically models the relationships among the variables as they change over time. And you have parameters in this model, the tunable things you can get to fit about how correlated different of those blue variables are to the orange variables and how quickly those correlations decay over time. And that gives you a way of taking historic data and predicting what's going on right now. Okay, let's see some plots. Enough of the description. Let's see some real data. Okay, so This is if you use the historic ratio metric to try to predict what the carbon dioxide level is in the blood. So we actually have, of course, measured carbon dioxide levels, but then you can ask, well, if I hadn't measured it and I instead used this model, what would my prediction have been? So along the horizontal axis is the actual observed partial pressure of carbon dioxide in the blood. Along the vertical axis is what this historic ratio model predicted. So if you're on the diagonal, you're nailing it. Exactly right. That's where you want to be. You want to be on the diagonal. If you're off the diagonal, okay, you made a bit of an error, okay? The red lines are where 80% of the points fall within the red bounds. Do they go this way, maybe? Okay, all right. And the green bounds is 95%. The gray squares are pertinent because less than, if the partial pressure of carbon dioxide is less than 35, then there's sort of a control rule, a thing you do to adjust the knobs. But if it's greater than 35, there's a different thing you do to adjust the knobs. And if it's greater than 60, there's even a different thing you do to adjust the knobs. So it's most important to get this right so that whatever the adjustment is would be the same adjustment. And so if the circle falls within the box, then in some sense, even if we're wrong, we're still going to make the same, medical decision. Okay. Now this is with the historic ratios. If we use our model that actually doesn't know too much about the blood, it just knows stuff about Gaussian processes, we get a tighter bounds here. Okay, fewer of these dots are outside of the boxes, and so that's very exciting. For the pH of the blood, it's a similar notion here. So again, there are three different things you can do, sort of leave things as they are, adjust this knob upwards or adjust this knob downwards. These are the thresholds. Here it is for the Henderson-Hasselbalch equations, which are the historic way care was administered. And here it is with a multivariate Gaussian process model of ours. It's again tighter. This slide just says if you look at our errors, that the error range we make is actually within the tolerances. If you were to have a clinical a laboratory equipment wanted to be certified, it's as accurate as that equipment needs to be. Now, most equipment's actually more accurate than that. And of course, it depends on historic blood gas values. So you can't just throw out taking blood gas values, but it does mean that on a moment by moment basis, you might be able to get out reasonable estimates so that you could adjust the knobs more quickly. All right, I just want to say this is a very small sample of 2 projects. There's a huge space of machine learning. There's even a huge space of healthcare and machine learning. The interface between machine learning and its application is critical. Hopefully I've drawn out here where it's really important to understand not just that I was trying to fit an equation, but why that equation was helpful and what equation should I even be trying to fit. Those were important conversations and why I spent 16 months at Children's Hospital Los Angeles with their pediatric intensive care unit. I find this fascinating. At the moment, I'm learning about cosmology because I'm working on a project in cosmology. I got to learn about medicine. I get to learn about cosmology. I get to learn about all these different things. It keeps my job very fresh and entertaining. So with that, hopefully I haven't gone too much over your scheduled time, but I'd be happy to take any questions if there are any. Yeah.
Yeah. So we have 2 questions from the audience.
Oh.
The first one is, will real AI reduce the number of computers required in an ICU?
That's a good question. Will it reduce the number? You're thinking about that picture with all those machines on it and whether or not, whether we reduce them. Probably not. It may consolidate them. It may make a larger computer. It'll probably just demand more compute time. The more complex a tool, a diagnostic tool you want, I don't think it'll reduce it. Certainly, this is a very cluttered scene. To make a point, oh, that's Bushra, that's not the scene. Where is it? Yeah, that's a very cluttered scene. You could do that all with a less cluttered environment, but I don't think the raw processing power or total amount of sort of compute there is going to go down. That would be unlikely.
Okay. Thank you for that. One more from our audience. Can the data from the PICU go live during the surgery, or are they meant to be stored as records?
This is a good question. And I'm going to answer it as somebody who spent a long time talking with people who work in this environment, but I didn't directly work in this environment. Actually, my little card allowed me to walk into the PICU, like I could get access to it. And I thought I shouldn't be here. Like I am not qualified. I'm qualified to talk to people who be here, but I'm not qualified to be here. My understanding is that it does get recorded. It typically doesn't go directly into the EHR data. So we do have recordings from anesthesiology records, for instance, from the middle of surgeries and things like that. It doesn't go directly into the EHR. Almost everything that goes directly into the EHR has to be approved by a human being. So at some point, there's some machine in here that's measuring the heart rate of this patient. That doesn't actually get automatically dumped into the EHR. Oops. Yeah, that would be like a high frequency measurement or a waveform. That's typically not dumped in the EHR, it's dumped someplace else. What's dumped is it usually comes up on the nurse's screen. You can't see it, but in at least in CHLA, oh, well, where is this picture? Right outside this room, this is there are two rooms, and right between them is a nurse station. A nurse looks after only two patients. It's the highest sort of standard of care. That nurse is looking at the thing and mentoring it in, hour by hour when something changes. So they usually don't get dumped directly in. There's a human who has to verify them.
Okay, thank you for that. And then we have a couple questions from our team. So
Sure.
The first one is, how is the data and privacy of the patients protected while developing these machine learning models?
Good.
And yeah.
Let me tackle that one first. I think that's a great question. The EHR data, you have to have approval to look at the EHR data. That's one reason I went to CHLA and worked there for 16 months. I did not, this data never entered computers here, for instance, at UC Riverside. So you have to be part of the team, one of the doctors who's authorized to do that. And then typically before even I would see it, although I could see it before this, you do some anonymization of it. There's some standards about what you can and can't what anonymization works and which doesn't. And that's kind of tricky. For instance, there are some patients in this database who were in the PICU for almost a year. Okay. If I told you I gathered data from 2000 to 2014, and here's a patient who was in there for 346 days, that pretty much uniquely identifies that patient, right? There aren't that many patients who stay in a PICU. Most of them are out in a couple of weeks, maybe a month. Okay, so you have to throw those out. You have to time shift things, so you can't tell exactly when they showed up at the ICU, because if someone admitted, on May 5th at 10 p.m., well, that might, narrow it down to a few patients if the medical records ever got out someplace, right? Which they never have, but if they did. So there are a whole series of standards that way. And then once we get into that form, then I start to analyze the data. Yeah, I hope that helps.
Yeah, and one last question. So for machine learning programmers working in healthcare, do the programmers need to have as in-depth knowledge of the medical field as doctors do? Or if not, how are solutions for those medical issues actually developed between the doctors and engineers?
Good, excellent. So I'm going to go back to this team down here, these 7 people, and there have been some others in and out. That's an engineering team. No, they did not have degrees that involve medicine or anything else. I think most of them have I'm trying to think. Well, Dave went on to get a PhD in this area, but the rest of them have bachelor's degrees in computer science or computer engineering or something like that. They work with the doctors. You on any project you work on, be it a word processor or anything else, right? As an engineer, you need to understand the users. In this case, the users are the clinicians, doctors, nurses, residents, that sort of things. And the patients, you need to understand them, you understand what they want, you go back and forth and try to resolve that. Of course, over time, you pick up some knowledge, right? So you pick up knowledge about how these particular medical databases work, because they're quirky in their own ways. You pick up knowledge about how doctors tend to work, because they're quirky in their own ways. You pick those things up, but none of these people had any training in that respect before they started those jobs. Yeah.
Okay, got it. So I think that's all the questions that we have, and we wanted to thank you for your presentation. It was really engaging. I know all of us enjoyed it a lot, and we really appreciate you taking the time to come speak with us today. So yeah, thank you.
It was really my pleasure. It was great fun to talk to or at all of you. If any of you find yourself at UC Riverside at any point, look me up, knock on my door, say hi. I'd love to chat more.
Okay, thank you so much. Have a
You're
great rest of
welcome.
the day. Bye-bye.
Thank you.
Okay, so let's move on to the award ceremony. I'm sure all of you have been, waiting for this moment. So a little bit about what this award ceremony is about. The AI Ideathon is a competition designed to challenge students to come up with novel ideas that apply AI to real-world problems. So this year's California AI Summit asked you guys to come up with ideas at the intersection of AI and healthcare. Projects were scored across 5 categories by our judging panel: project ambition and uniqueness, innovation, impact, feasibility, and presentation. And we received several submissions from teams all across the world, and we were very impressed with all of the projects. So great job. We will now announce the winners in each category. Okay, so the first award we will be presenting is the Best Design and UI Award, and this goes to Team Codebotics for their project Tootsie. So congratulations, Team Codebotics, for your project. And a little bit about Tootsie. Tootsie is an app which uses machine learning models to detect plaque on its user's teeth in a timely fashion and stores information on its user's dental health. We are particularly impressed by Tootsie's well-designed prototype and engaging graphics. So once again, really great job, Tootsie. Okay, so the next award that we will be presenting is the Most Creative Pitch Award. Now, this award goes to Janavi Tala for their project Artificial Intelligence Master Control. So this idea aims to provide more reliable health insights by integrating patients' medical history and drawing from existing health data. And we were particularly impressed with the ambition and scope for this project. So great job, Janavi. Okay, moving on. The next award is the Best Use of Neural Networks, and this one goes to Team ASH for their project, Understanding Teen Depression with National Survey Data. Great job, Team ASH. So a little bit about this project. It utilized public data on mental health in teens across several variables to draw novel insights on what factors could explain trends in depression. We thought that this project made thorough use of data analysis techniques such as hierarchical relationships and visualizations. So once again, great job, Team ASH. Okay, now the Best All-Girls Team Submission goes to the STEMinist for Symptom Stopper. Great job to the STEMinist. Symptom Stopper is an app designed to track environmental factors which may contribute to certain systems for individuals with autoimmune disorders. And we were particularly impressed by the STEMinists' idea to use association clustering to effectively find relationships between symptoms and environmental factors. So once again, great job to the STEMinist. Okay, so second place overall goes to Chinmayi Goyal for their project NewPie. So great job, Chinmayi. We were really impressed. NewPie is an original, low-cost, non-invasive method to detect Parkinson's disease. And we were particularly impressed with NewPie's model design that took several PD symptoms into account and alerted its users accordingly. Okay. So finally, first place overall goes to Team Doodlers for their project Smart Saver. So really great job, Team Doodlers. All of us were really impressed by your innovative project. So Smart Saver is a system designed to determine whether one can safely sit at a table in any sort of building. We really enjoyed the level of detail Team Doodlers put into their descriptions of how they would implement their project, as well as their project's huge scope for impact. Okay, so congratulations to all the winners. You all did a really great job. And if you want a prize, please stick around until the end because we'll be having a short meeting to discuss how you can receive your cash prize. Yep.
And on that topic, I do want to highlight that there is an attendee prize package for our winners. This was at the beginning of our slide that you could find here. So be sure to stay tuned for information on this. This is through our sponsors, which Krish will talk a little bit more about, and how you can receive these different awards and perks of being at this event today. Okay, so to conclude our event, I'd like to talk about some of our sponsors: Slingshot, Linode, REPL.IT, Balsamic, No Starch Press, and 1Password. We have received so much support from these different organizations and companies, and this really made this event possible. And we'd also love to thank deeply thank our speakers, Enrico Santos, Dr. Shelton, and Sarah Jerky, for their wonderful talks. And last but not least, we're super grateful to all of you guys, all of the participants who attended this event and submitted their project to the AI Ideathon competition. All the projects were marvelous, and we hope you continue to put forth innovative ideas. And we do want to note that even if you didn't win, please do not worry. Everyone who attended today's event will be eligible for a certificate of participation if you email us, and we'll be following up with a specialized, a unique certificate for you with your name and so forth. And with regards to the winners, those within the US will receive their prizes by the end of September. International students, as discussed previously, unfortunately will not be able to receive cash prizes, but they may choose to donate their prize money to a charitable cause or nonprofit. And we do want to note that through our sponsors, there are additional opportunities for our award winners. So for the people who fell under the best overall category, and you are of a certain age, we'll be sending you a link to an internship program with Slingshot, our sponsor right here, which is allowing for you to advance to the final stage of an internship program they host. So we will be following up with more information on that program. And I do want to note, I'm actually going to go back to this slide right here. So to elaborate on these different perks, you receive an extended trial to Balsamic Cloud, 1 free year of 1Password families, 1 free month of REPL.IT hacker plan, and a 20% discount code for ebooks. I highly recommend you take advantage of these opportunities. We'll be sending you things like codes and so forth just to specify how you will be able to redeem these different awards. And this applies to anyone, so everyone's a winner in the end, but if you did not get the chance to submit for the AI Ideathon competition. And basically, outside of all of these different opportunities, we also want to recommend that you apply to the Slingshot internship program, even if you didn't win. Apply to the Balsamic research program, where you can become more involved in their initiatives, or contribute to the 1Password open source project, which is basically an open repository of code where anyone can contribute. I highly recommend you push some code out there, or see if you would be able to recommend anything for their project. And these are just some opportunities that we would highly recommend you all get involved in. And let me drop a link in the chat for these opportunities. Oh, I see. Yashu has actually already linked these in the chat. So you would be able to open these and look more into it and find more information on each of these programs. And some GCL opportunities outside of this specific event today are the New York AI Ideathon submission. So this is due November 7th, and you would be able to qualify for $1,000 in cash prizes. It's basically a similar format of the California AI Summit. Please look at their criteria, because it will probably be a little different from our AI Ideathon criteria. But yeah, you can submit video pitches to the New York AI Ideathon, and after seeing the pitches today, that might inspire you to maybe submit to theirs also. And we also offer free STEM workshops to any student who wants to attend. GCL Scholars has been hosting workshops every single month where we have college students present on topics like Intro to Python, polymers, and front-end development. This is the next set of workshops happening over October, and I highly recommend you go ahead and sign up for those. It's very educational, it's interactive. You will be directly speaking with these scholars. They will lead you through these projects, and I just highly recommend you get involved in it. It's very exciting to see new topics in STEM that they will talk about. And I also want to mention that GCL is offering an opportunity for anyone who is in high school, middle school, etc., to apply to be a part of GCL. So if you really love this event and you're like, oh my gosh, like I really liked going to this event, and you go, I want to organize an event like this, you could have the opportunity to do that. So essentially you can apply for the chapter leaders program or and be assigned to a certain cohort depending on which state you're in, or you can apply to the national team, and we would have to follow up with you on more information on that. But in the chat, you'll notice, I believe we are just getting the link out to you right now, but yeah, you'll see under apply to GCL, you can get involved in GCL and some of the initiatives that we are running. And please note that the AI summits are just one of the core parts of GCL. There's so many other things. You could become involved in the STEM workshops, the GCL Scholars Program, our outreach programs, anything. We have multiple programs that could relate to your interests, so I highly recommend you apply, especially to those of you who were very interactive with this event today, because it's very exciting to be able to work with others on topics in STEM. So those are some opportunities within GCL. And for the closing, I would like for anyone who is an award winner to stay behind. We are just going to give a brief summary of how you could receive your prizes and how we will be reaching out to you. And thank you everyone for coming. I really appreciate all of you, all of the participants' time and effort. And we hope to see you in the future and possibly even as a GCL member one day. Thank you.
Before you leave, can you please,